हेलो एवरीवन। आज हम लोग देखेंगे इलेक्ट्रोकेमिस्ट्री। सो व्हाट इज इलेक्ट्रोकेमिस्ट्री? It's a branch of chemistry which deals with the study of conversion of chemical energy into electrical energy or electrical energy into chemical energy is referred to as electrochemistry. Okay, so and this is done through an electrochemical cell. So electrochemical cell it converts it converts chemical energy into electrical energy, chemical energy to electrical energy. Okay, the redox reaction, that is oxidation reaction occurring in an electrochemical cell is spontaneous, right? And involves a decrease of free energy of the system. So that's why it converts electrical energy into electrical energy. And remember that from chemical energy to electrical energy conversion, this is your spontaneous reaction. This is your spontaneous reaction. Okay, this is your spontaneous reaction. And the reverse process, that is conversion of electrical energy into chemical energy, electrical energy into chemical energy is also feasible, but the process is not spontaneous. So electrical energy to chemical energy conversion is non-spontaneous reaction. Okay, so today we learn about all these phenomena. Now, okay, before going deep into the chapter, remember that I have heard many people are confused about what reaction is happening at anode and what reaction is happening at cathode. So remember these short tricks, that is red cat and an ox. So in anode, oxidation reaction is happening, and in cathode, reduction reaction is happening. Okay, so remember this will help you in understanding the redox reaction. So red cat and ox. So in anode, oxidation reaction is happening, and in cathode, reduction reaction is happening. Now let us start our chapter with conductors and insulators. Conductors and insulators. So from electrical point of view, substances can be divided into two categories, that is electrical conductors and insulators. So what is electrical conductors? It is the substance which allow the passage of current through them. Those are electrical conductors or simply conductors. Okay, all metals and fused ionic compounds or their aqueous solution are the substance of electrical conductors. Gases also conduct electric current at low pressure when exposed to certain radiations. So remember this, gases also conduct electric current. So you should say electric current at low pressure, at low pressure or when exposed to certain radiations. Okay. Now, what is insulators? It do not allow the passage of electric current through them. Examples are rubber, glass, plastic, etc. Right? Certain substances like urea, sugar, or glucose dissolve in water, but their aqueous solutions do not conduct electric current. Such substances are also insulators, and we commonly name them as non-electrolytes. See, the conduction of current by a conductor is either due to flow of electrons or due to movement of ions, right? So we know this conduction of current by a conductor is either due to flow of electrons or due to movement of ions or due to movement of ions. So a substance can act as conductors only when it possesses either mobile electrons or free ions capable of moving in the solution. Right. Insulators do not have mobile electrons or free ions, hence unable to conduct electricity. Okay. We already know all these things, but it's a quick recapitulation because we will need these concepts. Now, moving forward to next topic is classification of electrical conductors. Classification of electrical conductors. See, electrical conductors broadly classified into two categories. One is metallic conductors and another is electrolytic conductors. So let me write it here. One is metallic conductors, one is metallic conductors, and another one is electrolytic conductors. Electrolytic conductors. Okay. Now see, all metals, let us say aluminum, zinc, copper, or alloys, that is bronze, steel, conduct electric current. Okay. So they possess mobile electrons which are responsible for conducting of current by them. The phenomena of conduction of current by metals is called metallic conductors. It's as usual, right? Or we can say electronic conduction. During the passage of electric current through a metallic conductor, no chemical change take place in the conductor because there is no movement of matter from one place to another. So remember this point. During the passage of electric current through a metallic conductor, metallic conductor, no chemical change, no chemical change take place, no chemical change take place in the conductor, in the conductor, because there is no movement, there is no movement of matter from one place to another. Okay, it is only the flow of electrons which conducts current. So the metallic conduction decreases with an increase in temperature. So remember this point also. Metallic conduction, metallic conduction decreases with an increase in temperature, because at that time collision between the electrons will also increase. So that's why if you increase temperature, metallic conduction will decrease. Okay. Now moving forward to electrolytic conductors, these points are for metallic conductors. Electrolytic conductors or electrolytes and electrolytic conduction. The conductors which conduct electric current on account of the electric on account of the movement of ions and undergo a chemical change during the passage of electric current through them are called electrolytic conductors. Okay. See, the phenomena of flow of current due to movement of ions, okay, is simply your electrolytic conduction. And these electrolytic conductors are ionic compounds and are also referred to as electrolytes. If you take some example, these are your electrolytic conductors NaCl, KCl, NaOH. These are your electrolytic conductors. Now, the electrolytic conductors or the electrolytic conduction is due to the movement of ions. Therefore, the ions must be free to move in order to conduct the current. This is why electrolytes are unable to conduct current in the solid state, because in solid state ions are not free to move, right? Electrolytes can conduct current only either in the fused state. Electrolytes can conduct current only either in the fused state or in aqueous solution. When electric current is passed through an electrolyte, either in the fused state or in the aqueous solution, ions move towards oppositely charged electrodes, that is cathode and anode, and a net chemical change takes place. The electrolytic conduction increases with an increase in temperature. I think all these things you know from your class 10 chemistry. If you don't know, we are revising it quickly in order to enter into the main topics of electrochemistry. Now, if we talk about classification of electrolytes, then it is classified as strong electrolyte and weak electrolyte. Before that, we have to know what is degree of dissociation. The conduction of current by an electrolyte in the aqueous solution is expressed in terms of degree of dissociation or degree of ionization. It is also known as degree of ionization. Remember that, degree of ionization. Okay. Now it is defined as the fraction of total number of moles which undergoes dissociation. That means number of moles undergoing dissociation or ionization divided by total number of moles. This is your degree of dissociation. The degree of dissociation of all electrolytes is not same. Depending upon the degree of dissociation, electrolytes can be classified into strong electrolytes and weak electrolyte. The electrolytes which dissociates almost completely into ions in solution are called strong electrolytes. That means we can say their degree of dissociation is almost 100%. Okay. Some strong acids like HCl, HNO3, H2SO4, these are strong electrolytes. Some strong bases such as NaOH, KOH, BaOH whole 2 are strong electrolytes. Some inorganic salts NaCl, KCl, BaCl2, NH4, NO3, these are strong electrolytes. If we take example, when 1 mole of KCl is dissolved in water, the resulting solution contains almost 1 mole of K plus ion and 1 mole of Cl minus ions, and practically no ionized KCl is left. Okay, so we can say that the ions remains solvated in solution. Since the solution of the strong electrolyte possesses only a very few unionized molecules at equilibrium, the equations for dissociation reactions for weak electrolytes can be shown as single arrow. Okay, it is shown by single arrow because in equilibrium there is no undissociated KCl, so there is no meaning of giving double arrow here. So KCl, 1 mole KCl breaks into 1 mole K plus and 1 mole Cl minus. That is 100% dissociation occurs. And if we take another example, HCl plus water, that is hydronium ion and Cl minus ion. In this case also it is 100% dissociation occurs. Now, if we talk about weak electrolyte, that means these electrolytes do not dissociate much in aqueous solution due to partial dissociation, that is, see here, degree of dissociation is less than 1. So we can say that the degree of dissociation is less than 1. Organic acids such as acetic acid, oxalic acid, benzoic acid, these are some of the organic acids which are weak electrolytes. Some of the organic bases such as CH3NH2, C2H5NH2, C6H5NH2 are your weak electrolyte. Some inorganic acids like HCN, H3BO3, NH4OH, COH whole 2, these are your HCN and H3BO3 are your inorganic acids, and NH4OH and COH whole 2 are your inorganic, some of the inorganic bases which considered as weak electrolyte. And if you take some example of inorganic salts, then it will be HgCl2, CH3, COO twice, Pb. These are your some of the inorganic salts. Okay, so you have to remember that weak electrolytes are mostly polar covalent compounds. Okay, remember this, weak electrolytes are mostly polar covalent compounds. Okay, and are weakly ionized in solution. Their solution contains both the ions as well as the undissociated molecules, and there is a equilibrium. See here, equilibrium sign is there. So if you talk about examples, then acetic acid in water, it will give hydronium ion and CH3COO minus ion, acetate ion. And if you talk about another example, that is NH3 aqueous plus H2O gives ammonium ion, NH3 plus aqueous and OH minus aqueous. Now let us see what are the factors which affects electrolytic conduction. The first factor is nature of electrolyte. The main point here is interatomic attraction. The nature of electrolyte decides the magnitude of interatomic attraction, or you can say solute-solute attraction, interaction, which plays an important role in deciding the extent of electrolytic conduction. If solute-solute interaction is high, there will be less dissociation of the electrolyte, and consequently electrolytic conduction will be less. In case of strong electrolyte, the solute-solute interaction is much less as compared to that of in case of weak electrolyte. This is why the aqueous solution of strong electrolytes conduct much more current as compared to those of weak electrolyte. Okay. Now our next point is solvation of ions. That is, the main point here is solute solvent interaction. If the ions are highly solvated in the solution, the electrolytic conduction is less. The solvation of ions depends upon solute solvent interaction. Higher the interaction between solute and solvent particles, greater is the solvation of ions and lesser is the current conducted by ions. So if you take example, the aqueous solution of LiCl conducts lesser current as compared to that of NaCl because smaller Li plus ions are more solvated than the larger Na plus ions. Okay, because this Li plus ion will attract more water molecules, polar water molecules towards itself, and it surrounds by more number of water molecules. That's why here solute solvent interaction is more. So it conducts LiCl conducts lesser current. Now our next point is viscosity of the solvent. That is solvent solvent. Your main point is solvent solvent interaction. Viscosity of solvent is also an important factors in deciding the extent of electrolytic conduction. Viscosity depends upon solvent solvent interaction. Larger the solvent solvent interaction, greater is the viscosity of solvent and lesser is the electrolytic conduction. Okay. Now our next point is nature of solvent and concentration of solution. So if we talk about this point, nature of solvent and concentration of solution, then we know that the polar and non-polar nature of a solvent is also important. Electrolytes dissociates to a greater extent in polar solvents, and we know water is a polar solvent, right? So electrolyte dissociates to greater extent in polar solvent, and we know that water is a polar solvent. This is why aqueous solution of electrolytes conduct more current as compared to their non-aqueous solutions. Now the concentration of solution is also important. Higher the concentration, lesser is the dissociation of the electrolyte into ions. This is very important point. Remember this. Higher the concentration, lesser is the dissociation of electrolyte into ions. So consequently, lesser is the current conducted by it. Now our next point is temperature. The magnitude of interionic attraction, solid solute interaction and solvent solvent interaction decreases with rise in temperature. Therefore, the electrolytic conduction increases with an increase in temperature, because here interionic attraction decreases, solid solvent interaction decreases, solvent solvent interaction decreases if you rise the temperature, if you increase the temperature. That's why you can say if temperature increases, conduction also increases. Now, moving forward to our next topic, which is electrolytic conductance. Now, see, we have just mentioned that metallic conductors as well as the electrolytic solutions are able to conduct electric current, right? The ease of flow of current through a conductor is referred to as its electrical conductance or electrical conductivity. The ease of flow of current through the electrolytic solution is termed as electrolytic conductance. Okay. Now, let us first see some important concepts related to electrolytic conductance. So, first is our Ohm's law. The potential difference across a conductor is directly proportional to the current flowing through it at a particular temperature. So, V is proportional to I. We can say V by I is constant, and that constant is your resistance, and unit is ohm. Okay. And we can define Ohm's law in another way also. The strength of current flowing through a conductor is directly proportional to the potential difference across the conductor and inversely proportional to the resistance of the conductor. Now, our next topic is specific resistance or resistivity. This is rho. So, we know that R is rho L by A, and this rho is your specific resistance. If we take L as 1 centimeter, area as 1 centimeter square, then from this equation we can see that resistance is your resistivity or specific resistance. Okay, so hence we can say that specific resistance is the resistance of the conductor having a length of 1 centimeter and cross section area 1 centimeter square. Okay, the specific resistance is also known as resistivity, and its unit is ohm centimeter. Okay, now our next topic is conductance. So, conductance is a measure of the ease of flow of current through a conductor. That means how easily current can flow through a conductor is conductance. So, it is defined as 1 by R. Conductance is C. C is inversely proportional to R, 1 by R. That means reciprocal of resistance is conductance, and unit of resistance is ohm. So, unit of conductance is mho, ohm inverse, that is we also refer to as mho or Siemens. Okay. Now moving forward to our next topic, which is specific conductivity or specific conductance or simply conductivity. This is your okay. This sign is the reciprocal of specific resistance, that is we can say resistivity, is known as specific conductivity or specific conductance or simply conductivity. See here, C is conductance and this kappa is conductivity, not conductance. Okay, conductance is reciprocal of resistance. Conductivity is reciprocal of resistivity. Okay, or specific resistance. That's what you have to remember. Okay, don't confuse yourself. Now see, we know the value of rho, that is R equals to rho L by A, R equals to rho L by A. So from here we can say that rho is RA by L. Okay, rho is RA by L. If we take 1 by R, see here 1 by R is conductance C, and if we take this L as 1 centimeter, length of the conductor is 1 centimeter, and area of cross section is 1 centimeter square, then conductivity is equals to conductance. Okay, so you can say that specific conductivity is the conductance of the conductor whose length is 1 centimeter and cross section area is 1 centimeter square. Okay, now see, a conductor of length 1 centimeter and cross sectional area 1 centimeter square having a volume of 1 centimeter cube, right? Because area into length, this is your volume. So a conductor which has length 1 centimeter, which has cross sectional area 1 centimeter square, that would have a volume of 1 centimeter cube. Okay, volume is 1 centimeter cube. Therefore, if an electrolytic solution is taken between two electrodes having area of cross section equal to 1 centimeter square and separated by a distance of 1 centimeter between the electrodes, let us say cathode and anode. Here distance between them is 1 centimeter and this cross section area is A. Cross section area of each plate is A. Okay, so this could be your volume of the solution, because in between them, if we draw the diagram, we can draw it in this manner. Let us say this is your conducting plates. Okay, now this is 1 centimeter and distance between these two plates is 1 centimeter. So if this side has the area 1 centimeter square and distance between the two plates is 1 centimeter, then cross section area multiplied by distance is your volume. So we can clearly see the volume of the solution in between these conductors is 1 centimeter cube, and the conductance of the solution will be equal to specific conductivity. Okay, specific conductivity, that is. So for an electrolytic solution, specific conductivity, this kappa, may be defined as the conductance of 1 centimeter cube of the solution. This is as simple as that. If we talk about unit of specific conductivity, then the unit would be per ohm per centimeter. Okay, or we can say Siemens per centimeter. Now our next topic is equivalent conductivity or equivalent conductance. This is represented as lambda equivalent. Okay? This is lambda equivalent of electrolytic solution. See, the conductivity of an electrolytic solution varies with the concentration of the solution. We know this, right? This is because the conductivity of an electrolytic solution is due to the presence of ions in it. The specific conductivity, just now we have defined that, is actually the conductivity of ions present in 1 centimeter cube of the solution, right? Just now we have defined. When concentration is changed, the number of ions present in 1 centimeter cube of the solution also changes, and consequently conductivity of the solution changes. In order to compare the conductivities of electrolytes, a new terms introduced, that is equivalent conductivity or equivalent conductance. Now the definition is equivalent conductivity is the conducting power of all the ions furnished by 1 gram equivalent of an electrolyte present in a definite volume of the solution. Okay, now if we see the relation between equivalent conductivity and specific conductivity, it is lambda equivalent is K by C equivalent. Okay, I will not always say couple, so for simplicity I will say K. So it is K by C equivalent. Here C equivalent is the concentration of the solution in gram equivalents per unit volume. Okay, so that means if 1 gram equivalent of an electrolyte is dissolved in V equivalent centimeter cube of the solution, then we can say that C equivalent is 1 by V equivalent gram equivalent per centimeter cube. Now if we put this value in this equation, then we will get lambda equivalent is K into V equivalent, because now C equivalent is 1 by V equivalent, so lambda equivalent would be K into V equivalent. Okay, now see, remember this V equivalent in this equation represents the volume in centimeter cube of the solution. Okay, this is volume in centimeter cube of the solution containing 1 gram equivalent containing 1 gram equivalent of the electrolyte. Okay, remember this. So on the basis of this equation, we can define equivalent conductivity or equivalent conductance lambda equivalent as it is. So equivalent conductivity or equivalent conductance of an electrolytic solution at dilution V equivalent is the conductance of the solution containing 1 gram equivalent of the electrolyte dissolved in V equivalent of the solution, V equivalent centimeter cube of the solution. Okay, now there is a relationship between equivalent conductivity and normality. That relation is V equivalent is 1000 by N centimeter cube. Remember, all of these equations are very important in order to solve questions. An electrolytic solution of normality N contains N gram equivalents, right, of the electrolytes dissolved per liter, that is 1000 centimeter cube of the solution. Therefore, 1 gram equivalent contains 1000 by N, and that is your V equivalent, and unit is centimeter cube. Now if we put this in this equation, we will get lambda equivalent is K times 1000 by N. And if you talk about the unit of lambda equivalent, it will be per ohm centimeter square per equivalent. Okay, or Siemens centimeter square per equivalent. Now moving forward to our next topic, which is molar conductivity or molar conductance, that is lambda m of electrolytic solution. Now see, the conducting power of an electrolytic solution can also be expressed in terms of a quantity. This is another quantity, molar conductivity or molar conductance. The definition is the conducting power of all the ions furnished by 1 mole of electrolyte present in a definite volume of the solution. This is the definition of molar conductance. Now if you talk about relationship between molar conductivity and specific conductivity, the relationship is lambda m is K by Cm, where Cm is the concentration of the solution in moles per unit volume. Okay, so we can say that if 1 mole of an electrolyte is dissolved in Vm centimeter cube of the solution, then Cm is 1 by Vm mole per centimeter cube. So you can clearly see that Cm is 1 by Vm, and if we put in this equation, then lambda m is K times Vm. Okay, this is your another relation. Here also note that here Vm represents volume in centimeter cube of the solution containing 1 mole of the electrolyte. Okay, just now we have seen the let us write it here. Vm is volume in centimeter cube, volume in centimeter cube of the solution containing 1 mole of the electrolyte. Okay, so Vm is volume in centimeter cube containing 1 mole of the electrolyte. So on the basis of this, we can define molar conductivity or molar conductance of an electrolytic solution at dilution Vm is the conductance of the solution containing 1 mole of electrolyte dissolved in Vm centimeter cube of the solution. That's all. Now, there is a relationship between Vm and molarity. Vm is 1000 by molarity. So you know an electrolytic solution of molarity M contains M moles of electrolyte dissolved per liter, that is 1000 centimeter cube. So 1 mole will one molarity, that is 1 mole contains 1000 by M, that is 1000 by M is your Vm. Okay, now if you put this in this equation, then lambda m will be K times 1000 by M, and the unit of lambda m is per ohm centimeter square per mole. Now there is a relationship between lambda m and lambda equivalent. Lambda m is your molar conductivity and lambda equivalent is your equivalent conductivity. And the relation is, we know that lambda m is K times 1000 by M and lambda equivalent is K times 1000 by N. So if you cancel this K and K, 1000 and 1000, it will be N by M. So you can simply say that lambda m molar conductivity by equivalent conductivity is normality by molarity, that is number of gram equivalent of electrolyte divided by number of moles of electrolyte. And if you further elaborate this will be mass of electrolyte by equivalent mass divided by mass of electrolyte by molar mass. So this will be molar mass by equivalent mass. The mass of electrolyte will cancel out. So it will be molar mass by equivalent mass. So from this we can say that lambda m is lambda equivalent times molar mass by equivalent mass. So this is a very important relation. Remember this. Now before moving forward to our let's move forward to our question. Our first question is, when a conductivity cell is filled with 0.02 normal aqueous solution of KCl, the resistance is 350 ohm. On filling the same cell with 0.1 normal sodium acetate, the resistance is found to equal to 1158 ohm. If the specific conductance of 0.2 normal KCl is given to 27.7 into 10 to the minus 4 per ohm per centimeter, calculate the equivalent conductance of sodium acetate solution. Okay, in order to solve this type of question, the first thing you have to know that Let us say we have a conductivity cell which looks like this. Okay. Let us say this is our one type of conductivity cell. There can be many types of conductivity cell. But whatever may be, in a conductivity cell, the distance L between the two electrodes, this distance, and area of the electrodes, this is the area of the electrodes, are fixed for a particular conductivity cell. So that means we can say that L by A is a constant for a particular conductivity cell, and this term L by A is known as cell constant. Okay, remember this. This is known as cell constant. Now, if we talk about, we know this relation, that is K is 1 by R into L by A. Now, L by A is cell constant, so we can say K is 1 by R is conductance into cell constant. Okay, remember these two equation because you will need in solving this type of question. Now, if we move forward to this question, just now we have seen that K is C times cell constant. So, cell constant is K by C, that is specific conductivity by conductance. Now, for KCl solution, resistance is given 350 ohm. Okay. Specific conductivity is given 27.7 into 10 to the minus 4 per ohm per centimeter. So, first calculate cell constant. C is 1 by R. So, the cell constant will be K times R. You know K and you know R. So, find out, it will be in 0.97 per centimeter. Now, see, it is given that calculate the equivalent conductance of sodium acetate solution. Normality given 0.01 normal sodium acetate solution, and resistance is given 1158 ohm. So, for sodium acetate solution, resistance is given, normality is given, cell constant we have just found it out, right, 0.97 per centimeter. So, again use the same formula. K specific resistance K is 1 by R into L by A and 1 by R into cell constant. So, you know resistance, you know cell constant, multiply, you will get the specific conductivity. So, it comes up to be 8.38 into 10 to the minus 4 per ohm per centimeter. Okay. Now, we know this relation, lambda equivalent is K times 1000 by N. K just now we have calculated and normality is given. So, if you calculate, you will get it as 83.3 per ohm per ohm centimeter square per equivalent. That is lambda equivalent. Now if we move forward to our next question, a solution containing 2 gram of anhydrous barium chloride in 400 centimeter cube of water has a conductivity of 0.0058 Siemens per centimeter. Calculate the molar and equivalent conductivities of the solution. So first of all, calculate the molecular mass of BaCl2. Molecular mass of Ba is 137, it is given, and chlorine we know 35.5, so multiplied by 2, you will get 208. Now what are the moles that is dissolved in 400 centimeter cube of the solution? That should be 2y, because we have 2 gram of barium chloride. So 2y 200. Weight by molecular weight is what is moles, right? So weight is 2 gram, molecular weight 208. If you calculate, you will get 9.61 into 10 to the minus 3. Now, what is molarity? Molarity would be moles of BaCl2 divided by total volume multiplied by 1000. So volume is 400 into 1000. You will get 0.024 molar. So first of all, we have calculated molarity of the solution. Now see, K is given, that is 0.0058 Siemens per centimeter, and we know this relation. That's why we have calculated molarity first, because we require this molarity. K is given, just put the values. We know molarity, we know K, you will get the answer, Siemens centimeter square per mole. Okay, now let's start our next topic, which is variation of molar conductivity with concentration. Now see, molar conductivity of an electrolytic solution, we know it in general it decreases on increasing concentration, but behavior of a strong electrolyte is somewhat different from that of a weak electrolyte. Now let's see variation of molar conductivity with concentration for strong electrolyte. If we talk about strong electrolyte such as ACl, HCl, this decreases slowly with an increase in the concentration. Okay. Now, experimentally, it has been found that at low concentrations, the molar conductivity varies slowly, varies linearly with the square root of the concentration. Here, यहाँ पे देखो हम लोग एक ग्राफ ड्रॉ किए हैं, but at higher concentration, the variation is not linear. Ideally, the graph should be this, linear, but at higher concentration, it is not linear. It will go in this manner. Graph will go in this manner. Okay. Now, molar conductivity of KCl, here molar conductivity of KCl has been drawn against the square root of the concentration. When the concentration is low, that is, concentration low means dilution is high, the curve is almost a straight line. See, up to this it is almost straight line. Okay, up to this it is almost straight line, showing a linear dependence of molar conductivity on the square root of the concentration. As the concentration increases, the curve is no longer a straight line. as the concentration of the solution decreases, that is, dilution of the concentrated solution increases, the molar conductivity of the solution of a strong electrolyte approaches a limiting value, and we can see that when concentration is 0, molar conductivity is lambda n infinite, that is at infinite dilution. Okay. Now, if delta C is 0, then molar conductivity is delta m infinity. Here it is delta m infinity. That is up to infinite dilution. A definite value of molar conductivity is obtained. This limiting value of molar conductivity when concentration approaches 0 is called molar conductivity at infinite dilution, that is delta m infinite. Now, we have just seen that when concentration tends to 0, your delta m is delta m infinite, right? The variation of molar conductivity with concentration for a strong electrolyte is found to obey this relation, which is delta m equals to delta m infinite minus b root c, where b is a constant. Okay, and c is the concentration of the solution, and this equation is known as Debye-Huckel-Onsager equation. From this equation, it is clear that if molar conductivity is plotted against square root of concentration, the value of delta m infinite for a strong electrolyte can be obtained by extrapolating delta root c 0, right? When root c is 0, that is when c is 0, then delta m approaches delta m infinity. Okay, I think you have got the point. Now, let us see our next topic, variation of molar conductivity with concentration for weak electrolyte. Now see, the dissociation of a weak electrolyte, let us say acetic acid, ammonium hydroxide, HCN, in solution is much less as compared to that of strong electrolyte. Therefore, the number of ions present in the solution of a weak electrolyte is much less than that of a strong electrolyte of the same concentration, right? Hence, the molar conductivity of a weak electrolytic solution is much lower than a strong electrolyte. From the graph, it is clear that this is your root C into 10 to the power 4 per mole centimeter cube to the power half is the variation of concentration. And here molar conductivity is in the y-axis. When the concentration of the solution of a weak electrolyte is lowered, that is dilution is increased, its molar conductivity increases, right? See, here molar conductivity increases slowly. First it is increasing slowly, then sharply at lower concentration. Okay, in this concentration, the molar conductivity value is very high. Thus, the variation of molar conductivity of a weak electrolyte with concentration is not linear, and the graph plotted between the values of molar conductivity delta m and square root of C for acetic acid. This is the graph between this, and from this graph it is clear that the graph is not a straight line, right? Showing that the variation of molar conductivity with concentration for a weak electrolyte is not linear. The molar conductivity increases sharply at low concentration, and the curve obtained in this case does not approach the lambda m axis when concentration tends to 0. Where for a strong electrolyte, when concentration tends to 0, we got a value that is delta m infinity. The value of delta m infinity for a weak electrolyte is obtained. This value of delta m infinity for weak electrolyte cannot be found out by direct method, but there is an indirect method which is known as Cole-Rush law. Okay, and from that Cole-Rush law, we will learn how to find delta m infinity at infinite dilution for weak electrolyte. Take solution. Now, if we see the explanation for the variation of delta m with concentration, see, weak electrolyte does not ionize much in solution. At moderate concentrations, only a few molecules of a weak electrolyte undergo dissociation into ions. Therefore, at moderate concentrations, the concentration of free ions in solution is much less as compared to that of a strong electrolyte. Due to low concentration of free ions in solution at moderate concentration, the molar conductivity of the solution of a weak electrolyte is quite low, and it is much lower than that of a strong electrolyte. As the concentration of the solution decreases, that is, dilution is increased, there is a steep rise in the molar conductivity, as it is clear from the graph for weak electrolyte. This is due to an increase in the ionization of electrolyte, otherwise it is not possible, right? As the solution becomes more and more dilute, more molecules of the weak electrolyte undergo dissociation into free ions, resulting in an increase in the molar conductivity of the solution. The sharp rise in molar conductivity at lower concentration is due to a sharp increase in ionization, right? So this is our main point. The sharp rise in molar conductivity at lower concentration is due to a sharp increase in ionization. Okay, that is due to sharp increase of number of ions, free ions. Now let's move forward to our next topic, that is Cole-Rush law. If we see in 1875, Cole-Rush studied extensively the molar conductivity at infinite dilution for a large number of strong electrolytes. He found that the difference between the values of delta m infinity for pairs of strong electrolytes having a common cation or a common anion is constant. Okay, he found it by experiment. Now if we see this table, here electrolyte is given and delta M infinity is given, and here difference is given. Okay, difference is given. Here also difference is given. And if we see the differences are constant, right? So from this table, it is clear that the difference between delta M infinity for each pair of electrolyte containing Na plus and K plus ion, irrespective of anions, here Na plus K plus, Na plus K plus, right? Whatever may be the anion present in them. Similarly, the difference between delta M infinity values for each pair of electrolyte containing Cl minus and Br minus, Cl minus, Br minus, Cl minus and Br minus ion is 2.06, irrespective of cations, right? Irrespective of cations present in them. This led Kohlraasch to conclude that each ion makes a definite contribution to the molar conductivity of an electrolyte at infinite dilution, irrespective of the nature of the other ion present in the electrolyte. Here anion does not create any difference, here cation does not create any difference. Okay. On this basis, Kohlraasch formulated an important law that is known as Kohlraasch law of independent migration of ions. And what is the law? The molar conductivity at infinite dilution of an electrolyte is equal to the sum of the molar conductivities of its cations and anions, with each conductance term multiplied by the number of respective ions present in the formula unit of the electrolyte. So let us say delta plus lambda plus infinity and lambda minus infinity respectively represents the molar conductivities of cations, and it represents lambda minus infinity represents molar conductivity of anions. Then according to Kohlraasch law, this lambda m infinity delta m infinity is mu plus lambda plus infinity mu minus lambda minus infinity. For lambda plus infinity we know molar conductivities of cations, lambda minus infinity we know molar conductivities of anion, and this nu plus is number of cations per formula unit of the electrolyte, and this mu minus is number of anions per formula unit of the electrolyte. Now if we apply this formula for HCl, we can say that delta m infinity here, because we have one cation H plus and one anion Cl minus, so this nu plus and nu minus will be 1 1. So we can write delta m infinity is lambda H plus infinity plus lambda Cl minus infinity. This is your anion, this is your cation. For BaCl2 we can write delta m infinity is here, if you see there are two anions, so it would be twice lambda Cl minus infinity, and there is one cation, so it is lambda Ba2 plus infinity. Now if we see aluminum sulfate Al2SO4 whole 3, this delta m infinity is there is 2 cation and 3 anion. So it will be twice lambda L3 plus infinity and thrice lambda SO42 minus infinity. This is as simple as that, right? So if we move forward, application of Coleridge law, the first thing is determination of lambda m delta m infinity for weak electrolyte, right? See, the value of molar conductivity is at infinite dilution, that is delta m infinite, for a weak electrolyte cannot be obtained by extrapolating delta m and root c curve, right? From the curve we know. However, delta m infinity values for weak electrolyte can easily be determined with the help of Coleridge law. If we take an example, the acetic acid, which is a weak electrolyte. So according to Coleridge law, delta m infinity of CH should be, there is one cation H plus and one anion CH minus. So it should be lambda H plus infinity plus lambda CH minus infinity, right? If the values of molar conductivities at infinite dilution for H plus and CH minus are known, if we know this, the value of delta m infinity can be found out. When the ionic conductances are not known, an indirect method is adopted. And in this method, a series of strong electrolytes, usually free electrolytes, is chosen in such a way that the sum or difference of their delta m infinities, lambda m infinities values give the delta m infinities value of the weak electrolyte under consideration. Let's understand this with an example. So it will be very clear. See, we want to find delta m infinity for acetic acid, right, which is a weak electrolyte. So for this, we have taken three strong electrolytes. One is HCl, one is sodium acetate, and one is NaCl. This is the indirect method of finding delta m infinity for acetic acid, weak electrolyte. Now see, delta m infinite HCl, we know from Coleridge law, we can write it in this manner. Delta m infinity for sodium acetate, we can write in this manner. Delta m infinite NaCl from Coleridge law, we can write in this manner. So what we can do, adding 2 and 3 and subtracting 4 from 2 and 3, we will get this. Delta m infinite HCl minus plus delta m infinite sodium acetate minus delta m infinite NaCl. So you have to add these two things and subtract this thing. So if you subtract this lambda Cl minus infinite, this is minus and this is plus, it will cancel out, and this Na plus infinite, this will cancel out. So ultimately we got lambda H plus infinite plus lambda CH0 minus infinite. Now we know lambda H plus infinite and lambda CH0 minus infinite is actually delta M infinite. So it is delta M infinite acetic acid. Okay. So that's how we can find delta M infinite for weak electrolyte, because we will know this value as they are strong electrolytes, right? So we can say delta M infinite acetic acid is delta M infinite HCl, delta M infinite sodium acetate minus delta M infinite NaCl. This is the biggest application of Kohler's law. Okay. Now, if we take another example, so delta M infinite of ammonium hydroxide can be found out by delta M infinite ammonium chloride plus delta M infinite sodium hydroxide minus delta M infinite NaCl. Okay. So here Cl and Cl will cancel out, and Na and Na will cancel out. So from this you can find out delta M infinite. So let us see one question regarding this. Question is, calculate the molar conductivities for ammonium hydroxide at infinite dilution if the molar conductances at infinite dilution for BaOH whole 2, BaCl2 and ammonium chloride is given. Okay. Now let's apply Kohler's law and see how to get the solution. See, delta M infinite ammonium chloride, we can write according to Kohler's law. Here one cation and one anion. It will be lambda infinite NH4 plus lambda Cl minus infinite, and delta M infinite BaOH whole 2 is lambda Ba2 plus infinite, and here two anions are there, so twice lambda OH minus infinite, and delta M infinite BaCl2 would be lambda Ba2 plus infinite plus twice lambda Cl minus infinite. So let us say this is our equation 1, this is 2, this is 3. So what we can do is multiplying equation 1 with 2 and adding with 2. So we will get twice delta M infinite NH4Cl plus delta M infinite BaOH whole 2 is actually you are multiplying by 2, so it would be twice this, twice this. So twice lambda NH4 plus infinite plus twice lambda Cl minus infinite plus lambda Ba2 plus infinite plus twice lambda OH minus infinite, right? Let us say this is our equation number 4. Now if we subtract equation 3 from 4, so let us subtract it. Twice delta M infinite NH4Cl plus delta M infinite BaOH whole 2 minus delta M infinite BaCl2 would be twice lambda NH4 plus infinite plus twice lambda Cl minus infinite plus lambda Ba2 plus infinite plus twice lambda OH minus infinite minus lambda Ba2 plus infinite minus twice lambda Cl minus infinite. So from this we can cancel out this thing, twice lambda Cl minus infinite plus twice lambda Cl minus infinite and lambda Ba2 plus infinite minus lambda Ba2 plus infinite. So ultimately we get twice lambda NH4 plus infinite plus twice lambda OH minus infinite. So we can say if we take twice common, it will be lambda NH4 plus infinite, lambda OH minus infinite, and this is our delta M infinite for NaOH, NH4OH, right? So it is twice delta M infinite for NH4OH. Okay. Now let us see. So we can say delta M infinite NH4OH would be half of this thing, right? Half of twice delta M infinite NH4Cl plus delta M infinite BaOH whole 2 minus delta M infinite BaCl2. So we know all the values, put it here. Half of twice delta M infinite NH4Cl is given 129.8 plus delta M infinite BOH whole 2, it is given 523.28 minus delta M infinite BaCl2 is given 280. So after calculation you will get 251.44 per ohm centimeter square per mole. That's how we can find out delta M infinite for weak electrolyte, and it's a very useful method. Okay, and its sums are extremely easy, right? You need only observation. Now next application of Kohlraasch law is determination of degree of dissociation of a weak electrolyte. Now see, molar conductivity of a weak electrolyte depends upon the extent to which it dissociates in solution, that is upon its degree of dissociation. As the dilution increases, the degree of dissociation of a weak electrolyte increases, right? As the dilution increases, the degree of dissociation of weak electrolyte will also increase. We know this. And this is accordance to the Ostwald's dilution law. Okay, this is accordance to Ostwald's dilution law, and consequently the value of the molar conductivity will also increase. At infinite dilution, the dissociation of a weak electrolyte is 100% and degree of dissociation is equal to 1. At this stage, the molar conductivity approaches a limiting value, that is known as molar conductivity at infinite dilution. If, let us say, this delta MC is the molar conductivity of a weak electrolyte at concentration C, and delta M infinite is the molar conductivity at infinite dilution. So degree of dissociation would be delta MC by delta M infinite. Okay. Now this delta M infinite for weak electrolyte can be find out by Cole's law. So we can write it as delta M C by, and we know from Cole's law it is mu plus lambda plus infinite, mu minus lambda minus infinite. So from this law, from this equation, we can find out degree of dissociation. Now let us see one example. Okay. The specific conductivity of a 0.1 molar NH4OH is 3.6 into 10 to the minus 4 per ohm per centimeter. The molar ionic conductances at infinite dilution for NH4 plus ion and OH minus ion are 53 and 198 per ohm centimeter square per mole. Calculate the molar conductance of the solution, degree of dissociation of 0.1 molar NH4OH, and dissociation constant of NH4OH. Okay. So let's calculate one by one. Now if we calculate molar conductance of the solution, now we know that delta M is K times 1000 by M. You know this relation. Now here K is given, that is 3.6 into 10 to the power minus 4 per ohm per centimeter. Molarity is given 0.1 molar. So delta MC, the specific concentration, right? So it will be 3.6 into 10 to the power minus 4 into 1000 by 0.1. If you calculate, you will get 3.6 per ohm centimeter square per mole. Now let us calculate degree of dissociation. Now see, from Cole's law we can say delta M infinite NH4OH is lambda NH4 plus infinite plus lambda OH minus infinite. Lambda NH4 plus infinite is given, infinite dilution for NH4 plus ion, and OH minus ion are given. So it is 53 plus 198, and this is your 251 per ohm centimeter square per mole. Now let us see number 3, dissociation constant of NH4OH. So if we calculate this, let us calculate number 3. See, NH4OH dissociates as, we know, it will be NH4 plus OH minus. Now at initial concentration, let us say initial concentration is C, and initially there is no NH4 plus and there is no OH minus. Now if we calculate at equilibrium, so concentration at equilibrium, if alpha is the dissociation constant, then it would be C minus C alpha, that is C common 1 minus alpha. It appears C alpha and it appears C alpha. And we know from mass action and law of equilibrium, dissociation constant, dissociation constant K is NH4 plus concentration of OH minus by concentration of NH4OH. Now this is C alpha, this is C alpha by C into 1 minus alpha. So this becomes 1 C will cancel out. So it will be C alpha square by 1 minus alpha. Now here C is given, that is 0.1 mole, right? So just now we have calculated that lambda m. Okay, let us first calculate this. This is your delta m infinite, right? So what will be your dissociation constant? That would be delta mc by delta m infinite, and delta mc is 3.6, delta m infinite is 251. So if you calculate, you will get 0.014. Okay, and the molarity is given 0.1 molar. Okay, and degree of dissociation of 0.1 molar. Okay, so concentration is given 0.1 mole per liter. Alpha we know 0.014, 0.014. Okay, now if you put these values in this, so K would be, this is not kappa, this is K. Okay, 0.1 into 0.014 square by 1 minus 0.014. If you calculate, you will get 1.98 into 10 to the power minus 5. This is the value of dissociation constant of NH4OH. Okay, degree of dissociation is alpha. This is your degree of dissociation, and dissociation constant is K. Now, number 3 application is determination of solubility of a sparingly soluble salt. The solubility of salts like AgCl, BaSO4, PbSO4 in water is so low that practically they are regarded as insoluble salt. Such salts are referred to as sparingly soluble salts. Since their solubility in water is very low, it is not possible to determine their solubility by the usual methods. However, from Kohlrausch law, we can calculate this. Since the solubility of a sparingly soluble salt is very low, its saturated solution is so dilute that it can be regarded as an infinitely dilute salt solution. Hence, the molar conductivity of a saturated solution of a sparingly soluble salt delta M saturation may be regarded as equal to the molar conductivity at infinite dilution, delta M infinite, and can be calculated according to Paul's law. Mu plus lambda plus infinite, mu minus lambda minus infinite. That is the first thing you have to know for sparingly soluble salts. Now, the specific conductivity of the saturated solution K sat, okay, K salt is specific conductivity of the saturated solution. Let us say that is K saturation is measured by the Wheatstone bridge method. This K saturation value is measured by Wheatstone bridge method. From the measured value, the specific conductivity of water used for the preparation of saturated solution is subtracted. Specific conductivity of water is subtracted. And this gives the net specific conductance of the salt, K salt. And molar conductivity is related to specific conductivity as delta M saturation is equals to K salt multiplied by 1000 by M, where M is molar concentration in mole per liter or molarity. Okay. Now what would be M? We know K salt. M would be K salt into 1000 by lambda M saturation. And we know lambda M saturation, that is mu plus this thing and mu minus this thing. So put the value, you will get molarity. So let's see one question to clarify the things properly. At 25 degrees Celsius, the specific conductance of a saturated solution of AgCl is this, and that of water is this. The molar conductance of infinite dilution for Ag plus and Cl minus ions are also given. Calculate the solubility of AgCl in gram per liter at the given temperature. So let's see the solution. See here given that lambda Ag plus infinite is 61.92 per ohm centimeter square per mole, and lambda Cl minus infinite is also given 76.34 per ohm centimeter square per mole. Now see AgCl is sparingly soluble salt, right? So its saturated solution can be regarded as an infinite dilute solution. Just now we have seen. So lambda M saturated should be equals to, sorry, delta M saturated should be delta M infinite, and this should be according with the Paul's law, because we have AgCl, so one cation, one anion. So it would be lambda Ag plus infinite, lambda Cl minus infinite. So we know all the values. Put it here. 61.92 plus 76.34. Okay. So you will get 138.26 per ohm centimeter square per mole. Now see, we know that kappa salt is kappa saturation. This is not K, this is kappa minus kappa water. Now we know K saturation. This is 3.41 into 10 to the power minus 6. It is given. And we know K water 1.61 into 10 to the power minus 6. So if you calculate, you will get 1.8 into 10 to the power minus 6 per ohm per centimeter. And we also know that delta M saturation is copper salt into 1000 by molarity. So from this we can say molarity is K salt into 1000 by delta M saturation. Now K salt we have just calculated 1.8 into 10 to the power minus 6 into 1000 divided by 138.26. We have calculated this thing also. So if you calculate this, you will get 1.3 into 10 to the power minus 5 mole per liter. Okay. Now solubility of AgCl is solubility of AgCl is 1.3 into 10 to the power minus 5 mole per liter. Okay. And now see molecular mass of AgCl is 143.5. Okay. So if we multiply it with 1.3 into 10 to the power minus 5 into 143.5, we will get, this is 1.3 into 10 to the minus 5, we will get 1.86 into 10 to the power minus 3 in gram per liter. Okay. Calculate the solubility of AgCl in gram per liter. This is the thing we have to calculate. So let's start our next topic, which is galvanic cell or voltaic cell. Very important. From now and onwards, you have to concentrate on each and every topics. The galvanic cell is a device in which chemical energy is converted into electrical energy. Okay. This galvanic cell is also referred to as voltaic cell after the name of Alessandro Volta, who devised the galvanic cell. Okay. And till now it is called Volta cell. Galvanic cell generates electric current on account of a redox reaction occurring on it. If you take some example of galvanic cell, these are Volta cell, Daniell cell, Lagrange cell, dry cell. These are the examples of galvanic cells. Now let us see the construction of a galvanic cell. The chemical process responsible for the production of electrical energy in a galvanic cell is always a redox process. Therefore, a galvanic cell can be constructed by uniting an oxidation electrode with a suitable reduction electrode. The solution involved in the two electrodes can be made in communication with each other either by a direct contact through a porous diaphragm in this diagram, and in outer circuit the two electrodes are connected to a device which is capable of utilizing the electrical energy produced. This is your outer circuit. At the oxidation electrode, the electrons get liberated due to oxidation process occurring at it. Okay. Now, uh, if not withdrawn, these electrons accumulate on the electrode and provide it a negative potential, that is anode. At the reduction electrode, that is cathode, a positive potential develops on account of the reduction process occurring at it. That is, it accepts electron. When the two electrodes are connected together, both in outer and inner circuits, electron starts flowing from the oxidation electrode to reduction electrode in the outer circuit due to the difference in potential, because here negative charge accumulates and here positive charge accumulates. Now see, thus an electric current is produced. The electrode at which oxidation process occurs is called anode, while at which reduction process occurs, that is takes reduction process occurs, is called cathode. Now here anode is of negative polarity and cathode is of positive polarity. Let us take example. If an oxidation electrode, let us say we have taken zinc rod. Now this zinc will oxidize and it will give 2 electron to produce Zn2 plus ion. Okay, to produce Zn2 plus ion. And if it is joined to a reduction electrode, that means this copper rod, it accepts 2 electron and reduce to copper. And this is the construction of a Daniell cell. Okay, this is the construction of a Daniell cell. Sorry, Da. This is the construction of a Daniell cell. The anode of this cell consists of a zinc rod dipped in the solution of zinc sulfate solution, and its concentration is C1. The cathode is made by immersing a copper rod in the solution of copper sulfate solution with concentration C2. The solutions of Zn2 plus and Cu2 plus ions are made in electrical communications either by a direct contact or through a salt bridge. Here direct contact is porous plate and here the contact is through salt bridge. This is a salt bridge. Okay. At the oxidation electrode, that is zinc rod, that is anode, zinc atoms pass into the solution because it leaves 2 electron, that's why it is oxidation. So zinc atoms, zinc ions will pass into the solution plus to E, it's leaving 2 electron, this zinc dot. While at the reduction electrode, that is cathode, copper ions changes into copper atoms. Now this here we have copper ions. So these copper ions, because we have copper sulfate solution, so in this we will have copper ions, Cu2 plus ions, and this C2 plus ions, this is actually for the zinc sulfate solution. From zinc sulfate solution we will have zinc will be reduced oxidized as Zn2 plus and plus 2E, and in the reduction electrode, copper ions changes into copper atoms, Cu2 plus ions, that is concentration is C2. From here it will accept 2 electron and reduce to copper atoms. Due to a potential difference, the electrons are set free on zinc rod, because electrons are accumulating here in the rod, and Zn2 plus ion is moving into the solution, ZnSO4 solution. Okay, so electron will accumulate in the zinc rod. So these electrons are set free on zinc rod and move towards the positively charged copper rod, and thus the current flows in the outer circuit. Now if we talk about the salt bridge, a salt bridge is a U-shaped glass tube filled with either a concentrated solution of an inert electrolyte such as KCl, okay, KNO3 or K2SO4, KCl or KNO3 or K2SO4, or the solidified solution of such an electrolyte in agar-agar and gelatin. The term inert electrolyte here refers to an electrolyte which neither takes part in the redox reaction occurring in the cell nor reacts with either of the electrolytes present in the two half cells. These are known as half cells. So if we talk about main function of salt bridge, it will be it completes the electrical circuits by allowing the ions to flow from half cell to another half cell, and another one is it maintains the electrical neutrality of the solution present in the two half cells. So these are two important points. Please write it down in your notebook so that when you will revise it will be very easy. I am not writing it here because writing everything will take a long time and the video length will be large. So write it down. If the salt bridge is not used, okay, the electrical balance of the ions in the electrolytic solution of the two electrodes will get disturbed. Let us take example. Let us consider the case of Daniell cell. Due to the oxidation process occurring at anode, zinc atoms changes into Zn2 plus ions, right, which pass into the solution, So here zinc rod from this Zn2 plus will pass into the solution and electron will accumulate in the zinc rod, that is at anode. At the same time, Cu2 plus ions present in the cathode solution. Here in the cathode solution we have Cu2 plus ions present in the cathode solution takes electrons and reduce into copper. Okay, here Cu copper will reduce, copper will accumulate in the outer side. Okay, which deposit on the cathode. Thus, during the operation of the cell, Zn2 plus ions accumulate in the anodic solution and a deficiency of Cu2 plus ions occurs in the cathodic solution. Thus, the anodic solution acquires an extra positive charge, that is Zn2 plus ion, and the cathodic solution an extra negative charge due to excess of SO4 2 minus ion, right? Here you will have SO4 2 minus ion, and here you will have Zn2 plus ion, extra Zn2 plus ion, and here you will have extra negative charge SO4 2 minus ion. This disturbs the electrical neutrality of the two solutions. The accumulation of positive charge around zinc cathode, okay, around the zinc electrode prevents the, if this zinc 2 plus ions accumulates in the outer side of the cathode, outer side of the anode, okay. So it will prevent the flow of electrons to the copper electrode. Similarly, the accumulation of negative charge around copper electrode, if this electron passes and negative charge accumulates in this, if negative charges accumulates here, prevents the flow of electrons to Cu2 plus ions, because these Cu2 plus ions needs electrons which are moving from zinc rod to cathode rod. Thus the flow of electrons is hindered and the cell stops working after some time. The salt bridge prevents the accumulation of excess charge around both anode, that is zinc electrode, and cathode, that is copper electrode. When the concentration of Zn2 plus ion in the anodic solution increases, sufficient number of Cl minus ions migrate from salt bridge to the anodic solution. Here from KCl, Cl minus ions will migrate into the solution. Okay, Cl minus ion will migrate in the solution to anodic solution and maintain the electrical neutrality in the anodic solution. Similarly, when the concentration of SO4 2 minus ion increases in cathodic solution due to reduction of Cu2 plus ions into copper atoms, sufficient number of K plus ions move into the anodic solution to maintain electrical neutrality. Okay, so this is the complete diagram of Daniell cell with a salt bridge, and this is the complete diagram of Daniell cell with a porous plate. Now let us talk about half cell. So our next topic is half cell. What is half cell? So a galvanic cell can be constructed by combining two electrodes, one being an oxidation electrode while the other a reduction electrode. Each electrode assembly is referred to as half cell. This is oxidation electrode, this is a half cell, this reduction electrode, this is another half cell. Thus a galvanic cell may be supposed to consist of a two half cells. The half cells in which oxidation process takes place is called anodic half cell or oxidation half cell. This is your oxidation half cell. This is your oxidation half cell. This is your reduction half cell or cathodic half cell. reduction half cell. Okay. Let's note here that the electrode at which oxidation takes place is called anode, and in a galvanic cell, anode is of negative polarity because electrons are accumulating here, while cathode is of positive polarity because CO2 plus ion is taking electron, so it will be positive polarity. So I think you have understood what is half cell. Now let us see how to represent a cell reaction of galvanic cell. So cell reaction of a galvanic cell. Here we have some IUPAC rules, and they have given some conventions. According to that, we have to represent the half cells. We have to represent the reactions. Number one is a half cell is represented by putting a single vertical line between the symbol of metal acting as electrode and the symbol of ion present in the electrolyte in contact with the metal. The vertical line represents the phase boundary. While writing the oxidation half cell, the reduced state is written on the left, whereas in the representation of a reduction half cell, the reduced state is written on the right hand side. So in this diagram, if you talk about IUPAC, how to represent. So for oxidation half cell, the reduced state is zinc. This is oxidized to zinc Zn2 plus. So reduced state is written in the left hand side. It's aqueous. So you can say this is your oxidation half cell anode. And if we represent this reduction half cell by IUPAC, it will be represented as the reduced state is for cathode is written in the right hand side. So CO2 plus aqueous will reduce to copper. This vertical line shows the boundary phase. Okay, so this is the representation of reduction half cell. Reduction half cell, that is cathode. Number two convention is, according to IUPAC, the molar concentration of the solution is written in the parenthesis after the formula of the ion. So let us say we have to mention the molar concentration. So that can be mentioned. Let us say Zn2 plus. So we have to mention within the brackets. Here let us say CO2 plus ion has the molar concentration C2, that is reduced to copper. So that's how we have to represent. This C1 represents the concentration of Zn2 plus ion, and C2 represents concentration of CO2 plus ion. Number 3 IUPAC representation is, see, while representing a galvanic cell, the oxidation electrode, that is anode, is always written at the left and the reduction electrode always at the right. Okay, direct contact of the two solutions, that is through a porous diaphragm, is shown by a vertical line, single vertical line, while the contact of the two solutions through a salt bridge is shown by a two parallel vertical line. So this is as simple as that. If there is a porous cell, then you have to join this by a single vertical line. That is, an oxidation electrode is written in the left, reduction electrode is written in the right. Okay, so this is your oxidation electrode with concentration C1, and here we have to give a single stroke. It is representing that we have the Daniell cell, there is a porous plate, and reduction electrode is written in the right. Okay, so anode is written in the left and cathode reaction is written in the right. So it represents the direct contact to a porous cell. And if you want to write or show it by a double stroke, then that means that there is a salt bridge. But always remember, anode in the left hand side, cathode in the right hand side. So Zn will be Zn2 plus C1. Here you will have to give a double stroke, and Cu2 plus C2 Cu. This is anode and this is cathode. So I think you got the point how to represent according to IUPAC. Now let us see the mechanism of production of electric current. So our next topic is the cell reaction. This is mechanism of production of electric current. Okay, let us see. The galvanic cell converts chemical energy into electrical energy. The chemical reaction responsible for the generation of electric current in a galvanic cell is a redox reaction. We already know all these things. This redox reaction is called the cell reaction of the given cell. So redox reaction is called the cell reaction of the given cell. So simply we have to write the redox reaction. So galvanic cell composed of two half cells, oxidation half cell and reduction half cell. The chemical process occurring at the oxidation electrode is oxidation and involves liberation of electrons. On the other hand, the process occurring at the reduction electrode is reduction and involves the gain of electrons. The cell reaction of a galvanic cell can be obtained by adding the oxidation and reduction reactions taking place at the anode and cathode in such a way that electrons get cancelled. So let us take one example for Daniell cell, so it will be more clear. So let us say we have at oxidation half cell, there is zinc is oxidized to Zn2 plus concentration C1 and it gives 2 electron. And if we write the reduction half cell, then Cu2 plus concentration C2, it taking 2 electron and it reduces to copper. Now Here 2 electron is in the right hand side, 2 electron in the left hand side, so it will cancel out. So our overall reaction would be zinc plus Cu2 plus with concentration C2 gives Zn2 plus with concentration C1 plus Cu. This is your net cell reaction. Net cell reaction. Okay. Now this redox reaction thus obtained is responsible for the generation of electric current in a Daniell cell. So you should know how to write these reactions. Let us see some example. So our first question is, write the half cell reactions. Write the half cell reaction and the net cell reaction and the net cell reaction corresponding to number 1 is Ni to Ni plus Ni2 plus, this is 1 molar double stroke, that means there is a salt bridge. Ag plus 1 molar Ag. So let's see how to solve this question. See here, let us first write the half cell reactions. So nickel is oxidized to Ni2 plus, which is 1 molar plus 2E, and the reduction half cell reaction is Ag plus 1 molar takes 1 electron and reduced to Ag. So what would be the net cell reaction? In order to get the net cell reaction, you have to cancel these electrons. So you have to multiply it by 2. So it will be nickel plus 2 Ag plus 1 molar, and this 2E and 2E will cancel out. This gives Ni2 plus 1 molar plus 2 Ag. This is your net cell reaction. Okay, this is your net cell reaction. Now our next question is, set up the galvanic cell corresponding to this reaction. So let us say Cu solid 2 Ag plus aqueous. This gives Cu2 plus aqueous plus 2 Ag solid. So let's see the solution. We have to set up the galvanic cell. Now this is a redox reaction, right? So from this we have to separate oxidation cell and reduction half cell. So oxidation half cell would be Cu solid, which will give Cu2 plus aqueous plus 2E. This is your oxidation half cell, and 2 Ag plus aqueous, it will take 2 electron and it will reduce to 2 Ag solid. This is your reduction half cell. Okay. Now see, oxidation process involves the copper solid to Cu2 plus aqueous. The anode reaction should be Cu solid according to IUPAC. You have to write the anode reaction in the left hand side. Single stroke Cu2 plus aqueous, and if we take the galvanic cell, so let us say we have a salt bridge and reduction electrode is written in the right hand side. Okay, so it will be Ag plus aqueous single stroke Ag solid. It will reduce to silver. So this is the setup of galvanic cell. Now our next topic is electrode potential. This is our next topic. See, galvanic cell can be set up by combining two half cells, one involving an oxidation process and the other in reduction process. The half cells used for this purpose are called single electrodes, and the reduction occurring at them are called half cell reactions. And oxidation occurs in the oxidation electrode, or we can say oxidation half cell, whereas the half cell involving reduction is called reduction electrode or reduction half cell. Potential developed on the electrode due to oxidation or reduction process is called single electrode potential or half cell potential, or simply electrode potential. The electrode potentials are responsible for the EMF of a galvanic cell. Now let us see the definition of electrode potential. This is the tendency of an electrode to lose or gain electrons when it is in contact with its own ions in solution is called electrode potential. When a metal is placed in contact with its ions, it usually possesses a tendency either to lose or to gain electrons. Okay. Now let us say a metal rod capital M is immersed in a solution containing its own ions. Let us say Mn plus ions. In such case, we have three possibilities. Number one possibility is the metal ion Mn plus collides with the electrode and undergoes no change. Number two possibility is a metal atom present on the electrode capital M loses n electrons and enters into the solution of Mn plus ions. That is, the metal atom is oxidized. And number 3 possibility is a metal ion Mn plus collides with the electrode, takes n electrons from the electrode and is converted into a neutral metal atom M. That is, metal ion is reduced. So oxidation is the possibility, reduction is the possibility, and collision is the possibility. So let us see one by one all these cases. So case 1 is when metal atom or ion undergoes no change. This is our first case. Okay. So if the electrode assembly is such that neither the metal atom nor the metal ion, that is Mn plus, undergoes any change, that is no oxidation or reduction process takes place at the electrode, no potential is developed. Okay. So here no potential is developed. Okay. Such an electrode assembly is called null electrode. This is known as null electrode. Now let us see our case 2, that is oxidation. When the metal atom gets oxidized, when the metal atom gets oxidized. Okay. Now if we see the diagram of null electrode, so let us draw it. We have a metal rod M here. This is the solution. This is your metal rod M, and in the solution we have Mn plus ions. Okay, Mn plus ions. So this Mn plus ions is colliding and leaving. So in this case we can say that there is no oxidation or reduction is happening. So this is the case of null electrode. Now case 2 is when the metal atom gets oxidized. So it will oxidize when it will lose electron. So let us say M loses n electrons and it gives Mn plus ions and n electrons. Okay. The ions Mn plus thus formed passes into the solution, and the electrons liberated in the oxidation process gets accumulated at the electrode. The process continues until the accumulated charge in the solution opposes further action. Thus, the electrode develops a negative potential, and the electrode assembly of this type is called oxidation electrode. If we see it in the diagram, let us say we have a metal rod. So this is your metal rod, and in the solution you have Mn plus ions, and this metal rod releases Mn plus ions in the solution, and all the electrons are leaving behind in the metal. This is your oxidation electrode. Okay, this is your oxidation electrode. Now let's see case 3. when the metal ion gets reduced. So if it gets reduced, let us say Mn plus ions aqueous takes n electrons and it is reducing to metal solid. This is known as reduction potential or reduction electrode. If we see it in the diagram, then we have a metal M dipped into the solution. This metal rod M, which is taking n electrons and reducing to M. Okay, and all the Mn plus ions are accumulating in this. It's going and taking n electrons. Okay, so the nature of potential developed on a particular electrode depends upon the relative tendencies of the metal atoms to get oxidized and the metal ions to get reduced. When the metal has a greater tendency to get oxidized, the electrode develops a negative potential. Electrode develops a negative potential due to accumulation of electrons on the rod. On the other hand, when metal ions possess a greater tendency to get reduced, the electrode develops positive ions. The electrode potential is actually the potential difference between the electrode and the solution. It is represented as E. Okay, the electrode potential is represented as E. The oxidation potential is represented as E oxy, or you can say this is E M2 Mn plus, while the reduction potential is represented as E reduction or E Mn plus to M. Now let us talk about standard electrode potential. Standard electrode potential. E naught. This is E naught. The potential of an electrode assembly is referred to as the standard electrode potential when it follows three conditions, and these three conditions I am telling you, please write it down. These are very important. Number one is the temperature of the electrode assembly is 298 Kelvin. Okay, let me write it here because these points are extremely important. The temperature of the electrode assembly is 298 Kelvin, that is 25 degrees Celsius. The number 2 point is the ion solution used in the assembly is of concentration 1 mole per liter. The ion solution used in the assembly is of concentration 1 mole per liter. Number 3 is the pressure of the gas. The pressure of the gas, if used in the assembly, is 1 atm. Okay, if these three conditions are satisfied, then only we can say that it is representing a standard electrode potential. It is represented by E naught. When the electrode potential comes into existence on account of an oxidation process occurring at the electrode in the standard conditions, the potential is said to be standard oxidation potential, and we can represent it by E naught oxidation or E naught M to Mn plus. Similarly, for a reduction process, it is referred to as standard reduction potential, and it is represented as E standard reduction or E naught Mn plus to M. For a particular assembly, the two potentials are numerically equal. However, their signs are opposite. Okay, their signs are opposite. E naught M to Mn plus is opposite sign of E naught Mn plus to M. Okay, so if we take one example, E naught Zn to Zn2 plus is of standard electron potential of zinc, is oxidation site is of opposite sign of standard reduction potential of zinc. Okay, so according to the IUPAC, the term standard potential should be used for the reactions written as reduction reaction. Therefore, the term standard potential or standard electrode potential is used for standard reduction potential. Okay, so let us move forward to our next topic. Now, let's talk about measurement of standard electrode potential. So our next topic is measurement of standard electrode potential. Okay, see, a single electrode is a half cell involving either an oxidation or a reduction process. Since oxidation and reduction processes are complementary, half cell reaction can never be carried out independently. Therefore, it is not possible to measure the absolute value of the single electrode potential of any single electrode. However, it is possible to measure the potential difference between two single electrodes. Therefore, the electrode potential of a particular single electrode can be measured only with respect to a standard reference electrode. Okay, and this standard reference electrode against which the electrode potentials of all other single electrodes are measured is the standard hydrogen electrode. And by convention, the electrode potential of hydrogen is assigned the value 0. Okay, so by convention, E naught half H2 to H plus and E naught H plus to half H2 is 0. Okay, now by this standard electrode potential, we can, this is the standard hydrogen electrode potential. By this we can measure other standard electrode potential. Now see, always remember the potential difference between the anode and cathode is a, in a galvanic cell, is the standard state. Okay, and that standard state is represented by E naught cell. So E naught cell is E naught cathode minus E naught anode. By this you have to solve questions. So remember this. Now moving forward to our next topic, which is electrochemical series. This is our electrochemical series. Okay. So if we talk about this electrochemical series, the method of finding standard electrode potential is we have omitted because we don't have the methods in our syllabus. But what you have to remember is the just standard electrode potentials of some compounds or atoms. So the standard electrode potential, that is considered as reduction potential, standard reduction potential of various electrode systems measured by the methods that are arranged in an increasing order. The arrangement of the obtained continuous and important series known as electrochemical series. So electrochemical series is the arrangement of various electrode systems in the increasing order of their standard reduction potential. Okay. So standard electrode potential means we have to represent it by standard reduction potential. Now see, this is the electrochemical series, and from this series you can notice that hydrogen, for hydrogen standard reduction potential is 0. Okay, this is the standard. So let us first see what the important features of electrochemical series, because this is very important. So first point is the electrode system having negative values of standard reduction potentials act as anode. So from this 0, if you move upwards, you will have more negative values. So that means these all negative values are acting as anode. Okay, when connected to a standard hydrogen electrode, while those have positive values act as cathode. So that means these are acting as cathode. This is your first point. Your second point is, on moving from top to bottom in the series, tendency to gain electrons. See what is done in the cathode. In the cathode, reduction happens, and in the anode, oxidation happens. That means losing of electron, and here in the cathode, gaining of electron. Right. So on moving from top to bottom in the series, tendency to gain electrons, that is the tendency for reduction to occur, increases. So from top to bottom, tendency to gain electron increases. The oxidized form of the substance placed at the top of the series, that is lithium, this lithium, or we can say lithium ion, possesses the minimum tendency to get reduced because it has the highest oxidizing power, right? So we can say that lithium plus ion is the weakest oxidizing agent. Okay. Now, on the other hand, it reduced form, that is lithium, this lithium will possess the maximum tendency to get oxidized. So, if we see that, see, lithium plus aqueous, if it gains electrons, then it will reduce to lithium ion. Lithium, it will reduce to lithium, and its standard reduction potential is E naught. Lithium plus to lithium minus is minus 3.05 volt. So we can say that, therefore we can say that lithium solid when oxidized, lithium plus aqueous plus electron is E naught. Lithium to lithium plus is, this is plus 3.05 volt. So we can say that lithium will act as the strongest reducing agent. It will be able to reduce any other substance placed below it. Okay. And number 3 point is, remember this, lithium is the strongest reducing agent. So it is the weakest oxidizing agent. On moving from the bottom to top, we move from bottom to top. In the series, the tendency to lose electrons, that is tendency for oxidation to occur, increases. The oxidized form of the substance placed at the bottom of the series, that is F2 gas, possesses the maximum value of standard reduction potential. This is the maximum value of standard reduction potential plus 2.87. Okay, this is plus 2.87. This means that it has the strongest tendency to get reduced. Consequently, F2 will act as the strongest oxidizing agent. So F2 is the strongest oxidizing agent. On the other hand, it reduced from F minus ion, reduced form is F minus ion, right? Will possess the maximum tendency to get oxidized. Therefore, F minus ion is the weakest reducing agent. So we can say F minus ion is the weakest reducing agent. So from this we can say that the oxidizing power of the oxidized form increases from top to bottom, and reducing power of the reduced form decreases from top to bottom. Okay. So our next point is, the reduced forms of the substance placed above hydrogen in the series are stronger reducing agents than hydrogen. Obviously, these are stronger reducing agents than hydrogen, while those placed below hydrogen are weaker reducing agent than hydrogen. The reduced form of any substance can reduce the oxidized form of any other substance placed below it in the series. That means nickel can reduce lead. Okay, copper can reduce iodine. Now let us see application of electrochemical series. Application of electrochemical series. See, our first application is reactivity of metals. Reactivity of metals. Remember, this is one of the most important part of electrochemistry because definitely one question will form from this section in any competitive exam or in your board exam. See, the reactivity of a metal depends upon its tendency to lose valence electrons. That is, its tendency to get oxidized. Greater the tendency of a metal to get oxidized, greater is its reactivity. Since in the electrochemical series, the tendency of the substance to get oxidized decreases from top to bottom, the reactivity of the metals decreases in going down the series. Right? So we can say reactivity of the metals decreases in going down the series. Because then they will not remove electrons. So less electrons means it is less oxidized. So less reactivity. The metal at the top possesses the minimum value of reduction potential because it has a minus sign. So it has the minimum value of reduction potential. Therefore, it will have maximum value of oxidation potential and will lose electrons readily. Therefore, it will be the most reactive metal. So let's see one question regarding this so that this topic will be more clear. The standard reduction potential values of 4 metals A, B, C and D are given minus 2.93, minus 0.25, minus 3.05 and minus 0.74 volts respectively. Arrange them in the decreasing order of their reactivity. Okay. Now see, we know that metals having lower value of standard reduction potential is more reactive, right? From this electrochemical series we know, and we have discussed a lot about this thing. The lower the value of standard reduction potential, the higher will be the reactivities. So what you have to do, you have to arrange this in decreasing order. So E naught reduction potential, if you arrange, it is minus 3.05, then minus 2.93, then minus 0.74, then minus 0.25. So it is the minimum value of standard reaction potential, so it will be highest. It will be the most reactive metal. So here this value is C, this value is A, this value is D, and this value is B. So this is the order. Okay. Now let's see our number 2 points, which is feasibility of a redox reaction. Feasibility of a redox reaction. See, the redox reaction is feasible when the substance having higher reduction potential gets reduced and the one having lower reduction potential gets oxidized. So let us see one example. Let us say we have a redox reaction, something like this. Fe2 plus aqueous plus Cu solid gives Cu2 plus aqueous plus Fe solid. Okay. So from electrochemical series, we can see that standard reduction potential of iron, that is this, is minus 0.44, and standard reduction potential of copper is, this is copper plus 0.34, right? So from electrochemical series, we can say standard reduction potential of V2 plus 2Fe is minus 0.44 volts, and standard reduction potential of Cu2 plus 2Cu is plus 0.34 volts. So you can see that this system Cu2 plus 2Cu has a higher value of standard reduction potential than Fe2 plus 2Fe. Therefore, the reaction would be feasible only when Cu2 plus ions gets reduced, right? So we can say that if we divide this redox reaction into two half cells, two half reactions, then it will be Fe2 plus aqueous will gain 2 electron to give iron. This is reduction, and Cu solid becomes Cu2 plus aqueous plus 2E. This is oxidation. Okay. Now, in the given reaction, we can see that copper is oxidized, whereas Fe2 plus ion are reduced. Since Cu2 plus 2Cu has higher reduction potential, that is plus 0.34 is higher than minus 0.44, the reaction is not feasible, right? This reaction is not feasible. Alternately, the feasibility of a redox reaction can also be predicted by calculating the value of inert cell corresponding to the given redox reaction, because we know that inert cell is inert cathode minus inert anode, right? If E naught cell comes out to be positive, the reaction is feasible. Reaction is feasible. And if E naught cell value comes out to be negative, reaction is not feasible. Reaction is not feasible. If E naught cell comes out to be 0, the reaction is in equilibrium. Reaction is in equilibrium. Okay. Now, in this reaction, the reaction given this redox reaction Fe2 plus aqueous plus Cu2 plus aqueous plus Fe. From this reaction, we can calculate E naught cell, that is E naught Fe2 plus 2Fe minus E naught Cu2 plus Cu. So you can say E naught Fe2 plus 2Fe value is minus 0.44 and this value is plus 0.34. So value comes out to be minus 0.78 volt. So that means reaction is not feasible, right? So this is the easy way of remembering this thing. So let's see one question regarding this topic. Predict whether the following reaction is feasible or not under standard conditions. Under standard conditions. So reaction is CO2 plus aqueous to twice Ag solid gave Cu solid plus twice Ag aqueous, and it is given that E naught Cu2 plus 2Cu is plus 0.34 volts and E naught Ag plus 2Ag is plus 0.80 volts. So if we split this reaction into two half reactions, then we will get Cu2 plus will definitely gains 2 electrons. C is aqueous, definitely gains 2 electrons to give Cu solid, and 2Ag solid will definitely lose 2 electrons to give 2Ag plus. Okay. So this is your reduction, that is at cathode. This is your oxidation, that is at anode. Okay. So you know that E naught cell is actually E naught cathode minus E naught anode. So that means E naught Cu2 plus 2Cu in cathode reaction minus E naught Ag plus 2Ag. at anode. So standard reduction potential at anode. Values are given. This is plus 0.34 minus plus 0.80. So value comes out to be minus 0.46 volts. So inert cell value is negative. That means we can say that reaction is not feasible. Now our number 3 point is displacement of metals, displacement of metals from salt solutions. Let's see this topic. See, in the solution, a metal is present in the form of its ions, that is in the form of its oxidized state. The displacement of metal from the salt solution involves the reduction of its oxidized form. So what is the oxidized form? Oxidized form of metal is Mn plus aqueous. This is your oxidized form, right? This is your oxidized form. It will gain n electrons and reduce to metal solid. So this is your reduced form. Okay. Since the reducing power of the reduced form, this form of a substance decreases in going down the series, the reduced form of a substance can reduce the oxidized form of any other substance placed below it in the series. Hence, a metal can displace any other metal placed below it in the series from the salt solution of the latter. Let's take one example to clarify this topic. When a zinc rod is placed in a solution of copper sulfate, zinc metal dissolves in the solution and copper gets precipitated. Right? We know this. So, if we see the reaction, Zn solid plus CuSO4 aqueous gives ZnSO4 aqueous plus Cu solid. Right? Or we can say Zn solid plus Cu2 plus aqueous gives Zn2 plus aqueous plus Cu solid. Now, this thing can be explained easily on the basis of electrochemical series. The standard reduction potential of two half cells, that is standard reduction potential of Zn2 plus 2Zn and standard reduction potential of Cu2 plus 2Cu. Zn2 plus 2Zn is minus 0.76 and Cu2 plus 2Cu is plus 0.34. So it is minus 0.76 volt and it is plus 0.34 volts, right? So obviously zinc is above copper in the series and possesses a higher reducing power than copper. Hence, zinc can displace copper easily. That's why we get ZnSO4. It displaces copper and takes the place, right? Because it is in the higher position in the electrochemical series than copper. Let's take one question to clarify the matter more. Arrange the following metals. Arrange the following metals in the order which they displace each other. Iron, copper, zinc, silver, magnesium and aluminium. So first of all, what you have to know, the standard potential or simply standard reduction potential from the electrochemical series. So I am writing it here. E naught Fe2 plus 2 Fe is minus 0.44 volts. E naught Cu2 plus 2 Cu is plus 0.34 volts. E naught Zn2 plus 2 Zn minus 0.76 volts. E naught Ag plus 2 Ag is plus 0.80 volts. E naught Mg2 plus 2 Mg is minus 2.37 volts, and E naught L3 plus 2 L is minus 1.66 volts. All the value written here are in the electrochemical series. Now if we arrange this metal in the increasing order of their reduction potential, so E naught in volts minus 2.37, then minus 1.66, minus 0.76, minus 0.44, plus 0.34, plus 0.80. And if we talk about metal, see, this is Mg. Okay. Similarly, this is for aluminium, zinc, iron, copper and silver. So this is the decreasing order of their reducing powers. So therefore we can say that magnesium can displace all, that is aluminium, zinc, iron, copper and silver from their salt solution. Aluminium can displace zinc, iron, copper, silver. Zinc can displace iron, copper, silver. Iron can displace copper and silver. Copper can displace silver, and silver cannot displace any one of them. Okay. Now let's see another question. Can a nickel spatula be used to stir a solution of copper sulfate? Okay, given that E naught Ni2 plus 2 Ni is minus 0.25 volt, E naught Cu2 plus to Cu is plus 0.34 volt. Now see here we can see the standard reduction potential of nickel is less than that of copper. Okay, so hence we can say that nickel has greater reducing power. More less value, more is the reducing power. Therefore, nickel can displace copper from copper sulfate solution. So we can say that Cu2 plus aqueous plus nickel solid gives Ni2 plus aqueous and Cu solid. Thus, a nickel spatula is used to stir copper sulfate solution will cause this reaction. So hence nickel spatula cannot be used to stir a copper sulfate solution because it reduced copper. Now our next topic, that is number 4, is displacement of hydrogen by metals from dilute acids. Displacement of hydrogen by metals from dilute acids. See, on the basis of electrochemical series, it can be predicted whether a metal will displace hydrogen from a dilute solution or not, right? Dilute acid or not. So, displacement of a hydrogen from a dilute acid is a reduction process. And if we talk about the reaction, it will be 2H plus aqueous, that is it will from acid, it comes from acid, plus 2E gives hydrogen gas. And we know standard reduction potential of hydrogen is 0 volts. This reduction process can be made to take place by a metal whose reducing power is greater than that of hydrogen, right? That is above the hydrogen. Since reducing power of the substances decreases going down from the electrochemical series, all the metal placed above hydrogen in the series possess higher reducing power as compared to that of the hydrogen. Hence, any metal placed above hydrogen in the electrochemical series can displace hydrogen from a dilute acid. In other words, metals having negative values of standard reduction potential can displace hydrogen from dilute acids, right? But metals below the hydrogen cannot liberate hydrogen gas. Let us see one question. Can dilute HCl, okay, let me write it here, can dilute hydrochloric acid be stored in a nickel vessel? Let's see. It is given that E naught Ni2 plus 2Ni is minus 0.25 volts. So from the data it is clear that, because we know standard reduction potential of hydrogen is 0.0 volts, so nickel reduction potential of nickel is less than that of hydrogen, so it possesses a greater reducing power than that of hydrogen and can displace hydrogen from dilute hydrochloric acid. Okay, so if we talk about reaction, it would be nickel solid plus 2HCl aqueous to give NiCl2 aqueous plus hydrogen gas, or we can say nickel solid plus 2H plus aqueous gives Ni2 plus aqueous plus hydrogen gas. So from this we can say that dilute hydrochloric acid cannot be stored in a nickel vessel. So our fifth number point is electropositive character. Electropositive character of metals and thermal stability of their oxides. Three, the electropositive character of a metal is its tendency to form positive ions by losing one or more valence electrons, right? The metal at the top of electrochemical series possesses the lowest value of reduction potential. Therefore, its oxidation potential would be the maximum and it will have the greatest tendency to lose electrons. Consequently, the metal at the top possesses the highest electropositive character. As the value of standard reduction potential increases in going down the series, the electropositive character of metals decreases. The thermal stability of a metallic oxide depends upon the electropositive character of the metal. Higher the electropositive character, greater is the stability of its oxide. Hence, the stability of oxides of metals decreases in going from top to bottom of the series. The oxides of lithium, sodium, potassium are very stable and do not decompose easily on heating, whereas the oxides of metals like silver, mercury, gold are not stable and decompose on heating, right? Because silver, mercury and gold, you see in electrochemical series, silver, mercury and gold. So mercury is here, sorry, this is lead. Gold, this is silver, and mercury, where is the mercury here? Sodium, potassium we can see, nickel, tin, lead, copper, oxygen, iron, silver, bromine, chlorine, this is manganese. Okay, mercury is not in the list. But it is there in the bottom. Okay. So from this discussion, we can see that, okay, The values are in between this, close to silver. So if we hit Na2O, it will have no change. And if we hit Ag2O, it will be 2Ag plus half O2. Because we have seen that the stability of oxides of metals decreases in going from top to bottom. So the silver is at the bottom side. So it is not stable. The oxide is not stable. But sodium is in the upper side. If you see here, sodium in the upper side, it has negative reduction potential. So it is stable. Right? Potassium is stable. Its oxides are stable. But oxides of silver, mercury, gold, these are not stable on heating. AgO. We heat, it will be 2Ag plus it will liberate oxygen. Now, our next point is number 6, which is calculation of the standard cell potential, that is inert cell. So you know that inert cell can be calculated by inert cathode minus inert anode. Okay, so this inert cathode and inert anode are the standard potential, that is standard reduction potential of cathode and anode. The values of inert cathode and inert anode can be obtained from electrochemical series, and if you know these values, you can calculate inert cell. Now, let us see one question. Question is, calculate the standard cell potential for the cell Ni, Ni2 plus 1 molar, Ag 1 molar, Ag plus 2 Ag. If E naught Ni2 plus 2 Ni is minus 0.25 volt and E naught Ag plus 2 Ag is 0.80 volt. So half reactions are Ni, Ni2 plus 1 molar plus 2E, that is oxidation, we can see, and 2 Ag plus 1 molar takes 2 electrons and reduce to 2 Ag. This is reduction. Okay, from this is reduction. So oxidation occurs at nickel electrode, while reduction occurs at silver electrode. So nickel should act as anode and silver should act as cathode, right? So from this it is clear that E naught cell, we know that it is E naught cathode minus E naught anode. So it should be E naught Ag plus 2Ag minus E naught Ni2 plus 2Ni. And value of reduction potential of nickel is minus 0.25 and silver is 0.80. So silver is acting as cathode. So 0.80 minus 0.25. So it is 1.05 volt is the value of inert cell. Now moving forward to our next topic, which is factors affecting electrode potential and Nernst equation for electrode potential. Let us see this. This Nernst equation is extremely important and you will definitely get one question from this. Now this electrode potential of an electrode assembly depends upon the nature of the metal and its ions. So let me write it here. This depends upon the nature of metal and its ions. Number 2, the concentration of ions, concentration of ions in the solution. Number 3 is temperature. These three are the factors which affects the electrode potential. When an electrode assembly is in the standard state, that is concentration of ions is 1 mole per liter, temperature is 298 Kelvin and pressure of the gas is 1 atm. The value of the standard electrode potential can directly be obtained from the electrochemical series. However, when an electrode assembly is not in the standard condition, that is its temperature is not 298 Kelvin, the ion concentration is different from 1 mole per liter and the pressure of the gas, if used, is different from 1 atm. Its electrode potential cannot be obtained directly from the electrochemical series, right? In such a case, the electrode potential of the electrode assembly can be calculated with the help of an important equation known as Nernst equation. So let us see what is Nernst equation. So Nernst equation correlates the electrode potential to the temperature of the electrode and the concentration of the species involved. Okay, so for an electrode involving the process of reduction, that is reduction electrode, Nernst equation can be written as E equals to T naught minus RT by NF log of reduced state upon oxidized state. Okay, Base, where this E is your reduction potential of the electrode assembly. This E naught is the standard reduction potential, standard reduction potential of the same electrode assembly. R is the gas constant, that is 8.314 joule per Kelvin per mole. T is the temperature of the electrode assembly. This is temperature of the electrode assembly. F is 1 Faraday, which is 96,500 coulombs. Okay, and this N is number of moles of electrons gained by 1 mole of the oxidized state, 1 mole of the oxidized state to get changed into the reduced state, in the process of reduction occurring at the electrode, occurring at the electrode. Okay, so here N is the number of moles of electrons gained by 1 mole of the oxidized state to get changed into the reduced state in the process of reduction occurring at the electrode. Now here reduced state and oxidized state, this concentration of oxidized state. This is concentration of the substance. Concentration of the substance undergoing reduction. Oxidized means it is undergoing in the reduction state. Reduction, right? So concentration of the substance undergoing reduction and this reduced state means concentration of the substance undergoing substance obtained on reduction. We should say concentration of the substance obtained on reduction. So let's take an example. If we say the electrode reaction is this, Mn plus aqueous plus Ne gives M solid. So this reaction, this equation is your main Nernst equation. This equation can be written as E naught Mn plus 2M E naught Mn plus 2M minus, this is E, not E naught. Okay, minus RT by NF log of M solid by Mn plus aqueous. Okay, so here Mn plus aqueous is the oxidized state because it is undergoing reduction process, and M solid is the reduced state because it is obtained on reduction. And since the concentration of a solid is taken to be unity, so we can say concentration of a solid is unity. So we can say Ms is 1. So now we can write this equation as E Mn plus 2M E naught Mn plus 2M. If we convert to log 10 base, it will be 2.303 RT by NF log 10 base Mn plus aqueous. Okay, now this equation, because we know that log of x base E is 2.303 log of x base 10. Remember this. This equation represents the relationship of the electrode potential, that is reduction potential, with the temperature and metal ion concentration, and may be used for the calculation of electrode potential of an electrode assembly at different temperatures and different metal ions concentration. Now we can change this equation into simpler forms. Okay, if T is taken to be equal to 298 Kelvin, now we are assuming that T is 298 Kelvin. This is the room temperature, right? Since most of the electrodes are set up and used at room temperature, right? A simpler equation may be obtained if this equation is calculated in room temperature. So we can say E Mn plus 2m is E naught Mn plus 2m minus 0.059 by n log of n 1 by concentration of Mn plus aqueous. So this is the simplified form of Nernst equation, and you have to remember this equation, not the earlier form, because it will help in calculation much faster. Here we have put the values of F and R and T at 298 Kelvin. So after calculation we get this equation. It is E naught Mn plus 2m minus 0.059 by n log 1 by Mn plus aqueous, concentration of Mn plus aqueous, base 10. This is your simpler form of Nernst equation. So let us take one question to apply this equation. Calculate the electrode potentials of the following half cells at 298 Kelvin. Number 1, Fe2 plus 0.1 molar 2Fe. Number 2, Pt H2 2 atm to H plus 0.02 molar. Given that E naught Fe2 plus 2Fe is minus 0.44 volt and E naught H plus 2 half H2 is 0.0 volt. Okay, so let's calculate. So first of all, see the half reaction. Okay, half cell reaction. This is number 1. Fe2 plus 0.1 molar. It will take 2 electron and reduce to iron. Okay, so here if you notice, we need the value of n. And what is n? N is number of moles of electrons gained by 1 mole of the oxidized state to get changed into the reduced state in the process of reduction occurring at the electrode. So how many electrons it gains? 2 electrons, right? So n is 2. And concentration of Fe2 plus ion is given, right? 0.1 molar. 0.1 mole. So according to Nernst equation, we can say E Fe2 plus 2Fe is E naught Fe2 plus 2Fe minus 0.059 by N log of 1 by concentration of Fe2 plus base 10. I'll put all the values. So this is 0.44 given minus 0.059 by 2 log of 1 upon 0.1 base 10. So 0.44, it is given that minus 0.44. Sorry, here we will have minus. And if you calculate this value, this is 1 by 10, right? That means log 10 base 10 is 1 and 0.059 by 2 is 0.0295. You calculate, you will get minus 0.4695 volt. Okay, this is the value you have to calculate. And if we see the number 2, that is H plus, C number 2, PT, H to 2 ATM to H plus. So here at H plus concentration is 0.02 molar, right? So H plus 0.02 molar, it will gain 1 electron and give half of H2 at 2 atm pressure. So here 1 electron is gained, so N is 1. And concentration of H plus is given 0.02 molar. And pressure is given is pH2 is 2 atm. Okay. Now see, from this we can say that according to Nernst equation, P equals to E naught minus 0.059 by N log of 10 base reduced state upon oxidized state. Oxidized state. So E H plus 2 half H2, that is E naught H plus 2 half H2 minus 0.059 by N log of, this is pH2 to the power 2 by concentration of H plus. Okay. Now we know all the values. Standard reduction potential of hydrogen is 0. That is 0 minus 0.059. 1 electron is transferred. So 1 electron is gained. So N is 1 log of 10 base. Pressure is 2 atm. Right? So it will be 2 to the power half divided by 0.02, the concentration of H plus. So if you calculate this value, it will be half will come outside and 2 by 2 will cancel out. So it will be 0.01. Okay. And 0.01 is 1 by 100. So it will be 10 square. So 2 will come outside. Log 10 base 10 is 1. So it will be minus 0.109. So moving forward to our next topic is EMF of a galvanic cell, that is cell potential. Okay. So the electromotive force of a galvanic cell, that is EMF of a galvanic cell, is defined as the difference of electrical potential which causes the flow of current from one electrode to another when virtually no current is drawn from the cell. This is the definition of EMF of a galvanic cell. In a galvanic cell, it is not possible to predict the direction of the flow of current because the direction of flow of current depends upon the relative tendencies of the electrons to supply or to remove the electrons. Therefore, it is necessary to follow a convention for describing the EMF and the reaction in a galvanic cell. The convention used, what is the convention? Convention is the EMF of a galvanic cell will be positive when there is a tendency for the electrons to flow from left to right in the external circuit. This is the convention. The EMF of a galvanic cell will be positive when there is a tendency for the electrons to flow from left to right in the external circuit. So the galvanic cells are therefore constructed according to the above convention. The oxidation electrode is always placed to the left hand side, while the reduction electrode is placed at the right hand side. Thus, the cell in which oxidations take place on the left hand side electrode and reduction at the right hand side electrode has a positive value of EMF. Now, if we calculation of standard EMF. See, according to IUPAC convention, the EMF of a galvanic cell is given by the following equation. E naught cell is E naught R minus E naught L. E naught cell is the standard EMF of the cell, that is standard cell potential. E naught R is the standard electrode potential of right hand electrode, that is cathode, and E naught L is the standard electrode potential or standard reduction potential of left hand electrode. So R stands for right hand electrode and L stands for left hand electrode, that is anode. So it is cathode minus anode. Okay, so let us see it by one example. If we have a Daniel cell, something like this, zinc Zn2 plus 1 molar, have a salt bridge, Cu2 plus 1 molar Cu. We know that E naught Zn2 plus 2 Zn is minus 0.76 volt, and E naught Cu2 plus 2 Cu is plus 0.34 volt. So according to IUPAC, we know E naught cell is E naught R minus E naught L. So E naught R means this value, right? This is right, this is left. So this should be plus 0.34 minus of minus 0.76. The value comes out to be 1.10 volt. Okay, I think you got the point. Now moving forward, Nernst equation for the EMF of a cell. We have already seen the Nernst equation in calculating the electrode potential of an electrode which is not in the standard state. This equation can also be used for the calculation of cell potential, that is EMF, of a galvanic cell whose electrodes are not in the standard state, right? So we know that E naught cell is ER minus EL, E naught L, or E naught cell is ER minus EL. The values of ER and EL can be calculated with the help of Nernst equation. And if you put those values, you can get E naught cell. Okay. Now let us see one by one. Number one is when the valencies of metals constituting the electrodes are similar. When the valencies of the metals constituting the electrodes are similar. Let us say we have a Daniel cell, zinc solid to Zn2 plus C1 to Cu2 plus concentration is C2 to Cu, where C1 and C2 represents the concentration of Zn2 plus and Cu2 plus ions, and in this case the valency of zinc and copper are same, right? 2, valency is 2, and here also valency is 2. So there is the heading, when valencies of metals constituting the electrodes are similar. In that case, your equation, Nernst equation, will be E cell equals to E naught cell minus 0.059 by 2 log of 10 base C1 by C2 volts. It is as simple as that. Remember this equation. If valencies of the metals are same, then simply C1 by C2. Now let's see number 2 points. When the valencies of the metals constituting the electrodes are different. Let us see one example. We have something like this: cadmium S to Cd2 plus C1 Ag plus C2 to Ag solid. So here we can see that the valencies of Cd is 2 and Ag is 1, right? So in that case, the important note you have to know that multiplication of electrode reaction by any factor does not change the value of E naught. So from this you have to know the relation, that is E cell is E naught cell minus 0.059 by 2 log of 10 base C1 by C2 square. There is a relation you have to remember. Okay. Now what will be the general expression? How to remember? Because we cannot make separate equations for every equation, right? So let us see our general expression. General expression for the EMF of a cell. If the solution used in the cell are dilute, activities may be replaced by concentrations. Remember this. If the solutions used in the cell are dilute, activities may be replaced by concentration, by concentrations. So our general equation would be E cell is E naught cell minus RT by NF ln C to the power R. See, our expression is this: E A plus QB is RC plus SD. Okay, sorry, this is a reversible galvanic cell reaction. Okay, it, so we can say from this that C to the power R, concentration of C to the power R into concentration of D to the power S divided by concentration of A to the power P into concentration of B to the power Q. or we can say P cell is E naught cell minus 2.303 RT by NF log of 10 base C to the power R D to the power S by A to the power P B to the power Q. Now if we take temperature 25 degrees Celsius, that is room temperature, and if we put the values of F, R and T, you will get P cell equals to E naught cell minus 0.059 by N log of C to the power R D to the power S by A to the power P B to the power Q base 10. So you have to remember this equation. So I think you got the point. Okay. Now let us take one example. So let us say we have a Daniel cell, zinc solid, zinc 2 plus C1, Cu2 plus C2 to CUS. So let us first write the half cell reaction, that is zinc solid will give Zn2 plus 2E. This is oxidation half cell reaction, and Cu2 plus C2 plus 2E gives Cu. This is reduction half cell reaction. So after cancelling 2E, we get ZnS plus Cu2 plus C2 Zn2 plus C1 CUS is the net cell reaction. Net cell reaction. Now see, this net cell reaction involves the transfer of 2 electrons. So from this we can say that N is 2. And from this equation, if we apply, we can say that E cell is E naught cell minus 0.059 by N log of concentration of Zn2 plus aqueous, concentration of Cu solid, because we have in the right hand side C and D, right? C and D, divided by concentration of Cu2 plus aqueous, concentration of ZnS. Okay. Now we know that concentration of a pure substance in solid state is unity, right? That is, you have to remember this concentration of a pure substance in solid state is unity. So this will be 1 and this will be 1. So we can say E cell is E naught cell minus 0.059 by n log of Zn2 plus aqueous by Cu2 plus aqueous base 10. Now if this concentration is C1 and this concentration is C2, then it is given that C1 is the concentration, C2 is the concentration. So we can say E cell is E naught cell minus 0.059 by 2 log of C1 by C2 base 10. Okay, I think we got the point how to calculate this type of, how to apply this type of formula. So let's see one question to clarify your all the doubts. Let us say the question is, for what concentration of Ag plus aqueous will the EMF of the given cell be 0 at 25 degrees Celsius if concentration of Cu2 plus aqueous is 0.1 molar. CuS Cu2 plus 0.1 molar. This is Ag plus aqueous, Ag solid. It is given that E naught Ag plus 2 Ag is plus 0.80 volt and E naught Cu2 plus 2 Cu is plus 0.34 volt. So let's see the solution of this question. So let us first write the net cell reaction from the information given here. So CuS gives 2 electron and becomes Cu2 plus ion, 0.1 molar plus 2E. This is at anode and 2 Ag aqueous will take 2 electron because we have to cancel out this electron, gives 2 Ag solid. This electron cancels out, is at cathode. So net reaction is Cu solid 2 Ag plus aqueous gives Cu2 plus 0.1 molar plus 2 Ag solid is a net cell reaction. Now from this it is clear that this reaction transfers 2 moles of electrons, right? So we can say N is 2. Now we know Nernst equation at 25 degrees Celsius, that is 298 Kelvin, is E cell is E naught cell minus 0.059 by n log of Cu2 plus aqueous by Ag plus aqueous, here coefficient is 2, so square, and for solid it will be 1, right? We know this. Cu solid concentration is 1, silver Ag solid is also 1. You know this, right? Now see, here question is given that for what concentration of Ag plus will the EMF of the given cell be 0. So it is given that EMF of the cell which is required 0. Now we know E naught cell is E naught R minus E naught L. So this should be E naught Ag plus 2Ag minus E naught Cu2 plus 2Cu. Okay, the values are given. This is 0.80 and this is 0.34. So this should be 0.80 minus plus 0.34. That is 0.46 volts. Okay. Now if you substitute these values into this equation, this is 0 equals to 0.46 minus 0.059 by 2 log of 10 base. This is 0.1 molar is given, 0.1 molar Cu2 plus, and we have to calculate Ag plus aqueous square because we have 2 moles, so here square. Now this should be log of 0.1 by Ag plus aqueous, which is 0.46 multiplied by 2 by 0.059, 15.593. Now if you take antilog on both the sides, then 0.1 by Ag plus aqueous square antilog 15.593 base 10. If you calculate, you will get this as 3.917 into 10 to the power 15. So from this, if you calculate Ag plus aqueous, it would be 5.05 into 10 to the power minus 9 molar. Okay, so let's move forward to our next topic, which is equilibrium constant from the Nernst equation. Okay, so you have to remember this equation, that is E naught cell is equals to 2.303 RT by NF log of Kc base 10. Now this Kc is your equilibrium constant, or we can say if we put the values at room temperature, then E naught cell would be 0.059 by n log of Kc base 10. Okay, this is the equation you have to remember. Now from this, if we know all the other values, we can calculate Kc, that is equilibrium constant. Now let's see one question regarding this. Question is, calculate the equilibrium constant of the reaction at 298 Kelvin. This is 2Fe3 plus SN2 plus 2Fe2 plus SN4 plus, given that E naught Fe3 plus 2Fe2 plus is plus 0.77 volt, and E naught SN4 plus to SN2 plus is plus 0.15 volt. R is 8.314 joule per Kelvin per mole, and F is 96,500 per mole. Okay, let's see the solution of this question. So if we see, so what is the oxidation and reduction of cell reaction? That would be SN2 plus aqueous, SN4 plus aqueous. This is oxidation half cell, and Fe3 plus aqueous to Fe2 plus aqueous. This is reduction half cell. So therefore we can say that our galvanic cell is SN2 plus aqueous to SN4 plus aqueous, Fe3 plus aqueous to Fe2 plus aqueous. Okay, now it can be clearly seen that two electrons are interchanged, so we can say N is 2, and we know E naught cell is E naught R minus E naught R minus E naught L. E naught R is your E naught Fe3 plus to Fe2 plus minus E naught SN4 plus to SN2 plus. So this is 0.77 minus 0.15, and this value is 0.62 volt. And let us say temperature is 298 Kelvin. Okay, so from this equation we can say that log Kc is E naught cell into Nf by 2.303 RT. Or we can say log Kc by 10 is N into E naught cell by 0.059. So log Kc base 10 is Nf E naught cell upon 2.303 RT, and if we put all the values, the N is 2, F is 96,500, E naught cell is, we have calculated 0.62 by 2.303 into R is 8.314 to 298. This is 20.97, and if you take anti-log, so Kc would be anti-log of 20.97. This would be 9.33 into 10 to the power 20. Now moving forward to our next topic, that is Gibbs free energy and EMF of a cell. Is very important. Gibbs free energy and EMF of a cell. Now see, we know that a galvanic cell converts chemical energy into electrical energy. When the cell operates, that is the cell reaction takes place, it does electrical work by transferring electrical charge through an external circuit. The electrical work done by the cell corresponds to decrease in the free energy of the system, that is cell's energy. There is a definite relationship between the free energy change for the cell reaction and the EMF, that is cell potential. When the cell does electrical work reversibly, that is only an infinitesimal current is drawn from the cell, the free energy change, that is delta G, is equal to the electrical work done. So we can say delta G is the electrical work done, is equal to electrical work done. Okay. Now from this equation we can say that when free energy change, that is delta G of the system, is negative, the system does electrical work on the surroundings. So from this we can say if delta G is negative, this implies the system work done will be negative. So we can, in that case we can say the system does electrical work on the surrounding. Okay, this results in the transfer of electrical charge into the outer circuit, that is the cell generates electric current. The situation corresponds to the operation of a galvanic cell to produce electric current. Now if we talk about number 2 point, when delta G is positive, we can say no electrical work is done by the system. that is no electric current is generated. So we can say no electrical work is done by the system. In other words, we can say no electric current is generated. However, the change can be affected only when the surroundings do electrical work on the system. Okay, and the situation corresponds to the process of electrolysis. So suppose the cell reaction occurring in a galvanic cell involves a transfer of n moles of electrons, and suppose E is the EMF of the cell. Therefore, the total charge involved in the cell reaction is n into F coulombs, where F is Faraday constant, right? F is 96,500 coulombs. So electrical work done by the system, we can say that electrical work done by the system is charge multiplied by EMF. Okay, and or we can say that W electrical is minus NF times E cell joule. Here work done by the system is taken as negative. Work done by the system is taken as negative, and this total charge involved, total charge involved in the cell reaction is given by n into F coulombs. Okay, that's why it is minus NF into E. EMF we have assumed that E cell. So we have to note that W electrical is the maximum electrical work that can be obtained from a galvanic cell. So we know that W delta G is W electrical. So from this we can say that delta reversible G is minus NF into E cell. Okay, and this delta RG represents the change in Gibbs free energy of the cell reaction. Now this is the relationship between free energy change and EMF of the cell. If the cell operates under standard conditions, this is the actual equation. Now, if the cell operates under standard conditions, that is, all reactants and products involved in the cell reaction are in the standard states, in that case, we can say that delta R G naught is minus NF E cell naught. This is in the standard conditions, where E naught cell is the standard EMF of the cell and delta R G naught is the standard free Gibbs energy with the standard EMF of the cell. In fact, the standard free energy associated with the standard EMF of the cell is the standard free energy change for the cell reaction. Now, let us talk about next topic, that is free energy change and equilibrium constant. Okay. See, we already know that E naught cell is 2.303 RT by NF log of Kc base 10. If you put the value of E naught cell into this, we will get delta R G naught is minus NF multiplied by 2.303 RT by NF log of Kc base 10. So this will cancel out. So ultimately we got delta R G naught is minus 2.303 RT log of Kc base 10. This is the relation you have to remember. This is the relationship between delta R G naught and Kc, equilibrium constant of the cell reaction, and may be used for the calculation of the value of Kc provided the value of delta R G naught is known. Okay. So let us see one question regarding this. So this topic will be more clear to us. The question is, calculate the maximum possible electrical work that can be obtained from the following cell under the standard conditions, under the standard conditions at 25 degrees Celsius. Okay, this is Zn2 plus aqueous, Sn2 plus aqueous, Sn at 25 degrees Celsius. If E naught Cu2 plus 2Cu is given as 0.76 volt and E naught Sn2 plus 2Sn is 0.14 volt and F is 96,500 coulomb per mole. So let's see the solution. From the given cell reaction, we know that E naught cell is E naught R minus E naught L. So it should be E naught Sn2 plus 2Sn minus E naught Zn2 plus 2Zn. Okay. Now Sn2 plus 2Sn, this value is given as 0.14. Here I think it is Zn2 plus 2Zn. Okay. Now this value is minus 0.14 and minus this value is also minus 0.76. So it will be 0.62 volt. Okay. So the cell reaction would be Zn solid plus SN2 plus aqueous, Zn2 plus aqueous plus Sn solid. So from this reaction we can see that transfer of 2 electrons, 2 moles of electrons. So N is 2. So we can say delta R G naught is minus F minus NF E naught cell. This would be minus 2 multiplied by 96500 multiplied by 0.62, and this is minus 119660 joule per mole. Okay. Now this is minus 119.66 kilojoule per mole. Since the standard free energy change for the cell reaction is equal to the maximum electrical work done by the system, the maximum electrical work done that can be obtained from the given cell as minus 119.66, because we know this relation, that is delta G is W electrical. Okay, and this is the thing you have to calculate. So what is the work done? Electrical, this should be 119.66 kilojoule. Okay, now let us see our next topic, which is EMF of a cell and feasibility of the cell reaction. So let's see EMF of a cell and feasibility of the cell reaction. See, a spontaneous reaction occurring at constant temperature and pressure proceeds in the direction in which free energy of the system decreases. Right? So we know this. Spontaneous reaction occurring at constant temperature and pressure proceeds in the direction in which free energy of the system decreases. That is, we can say delta G is less than 0 at constant temperature and pressure. Okay, a cell reaction occurs at constant temperature and pressure and is spontaneous. Therefore, a cell reaction should proceed in the direction in which Gibbs free energy decreases. So, in other words, we can say that a cell reaction is feasible only when delta G is negative for it. Remember, this is an extremely important point. Now, we know that delta Rg is minus Nf into E cell. If the cell operates under standard conditions, in that case, we can say delta Rg naught is minus Nf E cell E naught cell. On the basis of these equations, the feasibility or spontaneity of the cell of a cell reaction can be discussed. So let us discuss it one by one. So when E cell or E naught cell is positive, okay, so when the EMF of the cell or cell potential is positive, we can see that delta G naught is negative, right, because N and F is always positive. Hence, when a cell potential is positive, the cell reaction is feasible and the reaction occurs spontaneously. Number 2, when E cell or E naught cell is negative. So from this equation, you can say that if E naught cell is negative, delta G would be positive. Okay, that is, we can say that the cell reaction will not be feasible because delta G here is positive, and the cell reaction will not occur. Now next point, when E cell or E naught cell is 0, so we can say in that case delta G naught will be 0. That means the cell attains its equilibrium. Okay, this is a condition of equilibrium. So remember this. Now let us see one question regarding this so that it will be cleared completely. Predict whether the following reactions under standard conditions are feasible or not. So let us see. This is number 1, Ni solid, 2H plus aqueous. This is Ni2 plus aqueous plus H2 gas. Number 2 is 2Cl minus aqueous plus I2 solid gives 2I minus aqueous plus Cl2 gas. And given that E naught Ni2 plus 2Ni is minus 0.25 volt. E naught H plus 2 half H2 is 0 volt. E naught half Cl2 to Cl minus is plus 1.36 volt, and E naught half I2 to I minus is plus 0.54 volt. So let's see it one by one. So what would be the galvanic cell corresponding to number 1? That would be nickel solid to Ni2 plus aqueous, H plus aqueous to half H2 gas. Okay. So for this cell, we can say that E naught cell is E naught R minus E naught L. So it would be E naught H plus to half H2 minus E naught Ni2 plus to Ni. So this would be 0 minus of minus 0.25, that is plus 0.25 volt. And we know that delta R G naught is minus NF E naught cell. So here C E naught cell is positive. So this implies delta R G naught is negative. So that means this reaction is spontaneous and feasible. Now if we talk about number 2, we are judging all this by the standard reduction potential. And for number 2, the galvanic cell would be Cl minus aqueous to half Cl2 gas. This is half I2 solid to I minus aqueous. Okay. So for this cell we can say E naught cell is E naught R minus E naught L. That is E naught half I2 to I minus E naught half Cl2 to Cl minus. Okay. So this should be plus 0.54 minus or minus 1.36, and this value is plus this value half I2 to I is given as positive, and half Cl2 to Cl is positive. It's not negative, this is positive. So it will be minus 0.82 volt. So here we can see that E naught cell is negative, and we know delta R G naught is minus NF E naught cell. So if this is negative, delta Rg would be positive, because negative or positive. So this implies delta G naught is positive. So that means the reaction is not feasible. Okay. Now moving forward to our next important topic, that is electrolysis and criteria for product formation. So let's move forward to our new topic, which is electrolysis and criteria for product formation. Okay. Now see, galvanic cell, also called an electrochemical cell, converts chemical energy into electrical energy, right? The reverse process, that is the conversion of electrical energy into chemical energy, is also possible. The cell which converts electrical energy into chemical energy is called electrolytic cell, and the process which converts electrical energy into chemical energy is called electrolysis. Okay. Now let us see electrolytic cell and electrolysis. So first see electrolytic cell. Okay. So first let us draw a diagram. Diagram would be same, but the actions are different. Okay. This is your positive side, this is negative, this is the battery, this is your anode, this is your cathode, and this is your electrolytic solution of electrolyte. So see, we know that an electrolytic cell is a device in which electrical energy is converted into chemical energy through the process of electrolysis. The process of electrolysis involves the passage of current from an external source into the solution of electrolyte. Therefore, an electrolytic cell consists of suitable arrangements to pass electric current in the solution of an electrolyte. Okay, this is one such type. It consists of an electrolytic tank. This is your electrolytic tank, made of some non-conducting material like glass, bakelite, etc. The solution to be electrolyzed is filled in the tank. This is your solution of electrolyte. The electrolyte can also be taken in the fused state. The cell consists of two metallic rods. or graphite rods dipping in the solution of electrolyte and connected to a battery. These rods act as electrodes. The rod connected to the positive terminal of the battery act as anode. See, here this terminal is connected to positive side, so this is anode. While that connected to the negative terminal of the battery is cathode. It is to be noted here that anode is an electrolytic cell is of positive polarity, while the cathode is of negative polarity. Okay. Now let us see what is electrolysis. Electrolysis. Electrolysis is the process which involves the conversion of electrical energy into chemical energy. In this process, electrical DC current from a galvanic cell or a battery is passed through the electrolyte taken in an electrolytic cell either in the form of an aqueous solution or in the fused state. Ions present in the solution of electrolyte migrate towards oppositely charged electrodes under the influence of electric current and get discharged at them. So here positive charge will migrate towards cathode and negative charge will migrate towards anode. Okay. Thus the electrolyte gets chemically decomposed into the species obtained at the two electrodes. Electrolysis, so you can define electrolysis as a process which leads to a chemical change on the passage of electricity through an electrolyte present either in the dissolved state or in the molten state. Now if we see the mechanism of electrolysis, let us see the mechanism of electrolysis. Let us see this. See, the process of electrolysis can be explained on the basis of theory of ionization. According to the theory of ionization, an electrolyte dissociates into two types of charged particles called ions in the solution. The positively charged particles is called cations, while the negatively charged particles is called anions. The ions are also present in the fused state of an electrolyte. These ions move randomly in the solution as well as in the fused state of the electrolyte. When electric current is passed through the solution or through a molten electrolyte, the random movement of the ions ceases and they begin to move towards oppositely charged electrodes, right? The cations move towards cathode and the anions move towards anode. On reaching the respective electrodes, the ions get discharged either by taking electrons from the electrode or by giving electrons to the electrode and change into neutral species. The cations take electrons from the cathode. Here cation will take electron from the cathode and thus undergo the process of reduction at cathode. On the other hand, anions transfer electrons to the anode. Here anions will transfer electrons to the anode and undergo the process of oxidation at anode. The conversion of ions into neutral species is called primary change or primary process. The neutral species formed in the primary process may be collected as such at the respective electrodes or may react further to form the final product. And this is called secondary change or secondary process. Now, let us see by one example. Let us understand the process by one example. Electrolysis of molten sodium chloride. Let us see this. When electric current is passed through the molten sodium chloride, sodium is deposited at the cathode and chlorine is liberated at the anode. So in molten state, we can say NaCl, molten. In molten state, it will dissociate into Na plus and Cl minus. On passing electric current, Na plus ions move towards cathode because it is positively charged. Na plus will move towards cathode and Cl minus towards anode, right? Na plus will move towards cathode and Cl minus towards anode. Each Na plus ion takes an electron from the cathode and gets reduced into Na, whereas each Cl minus ion give an electron to the anode and gets oxidized into Cl atom. Since Cl atom cannot exist independently, they combine together to form Cl2 molecules. Okay. Now we can write the reaction at cathode and anode. So at cathode, Na plus ion takes one electron and it reduces to sodium atom. This is the reduction at cathode. And at anode, Cl minus gives one electron and it reduces to Cl. This is your oxidation, and you can say this is primary change. Primary change. Now this Cl atom cannot exist single atom. So Cl plus Cl will be Cl2 gas. This is your secondary change. This is your secondary change. So on account of electrolysis of fused sodium chloride, sodium is obtained at cathode and chlorine gas is obtained at anode. Right? Now let us see what is the criteria of product formation. Criteria for product formation. Criteria for product formation. The above mentioned mechanism helps a lot in predicting the nature of products obtained in the electrolysis of fused salts. However, the situation becomes complicated in case of the electrolysis of aqueous solution of the salts, and the above mechanism does not help much. Let us take an example. On electrolysis of a concentrated aqueous solution of sodium chloride, hydrogen gas is obtained at the cathode instead of sodium as in the case of fused sodium chloride. Therefore, it becomes necessary to explore necessary criteria which could predict and explain the nature of products obtained during electrolysis of aqueous solutions. Okay. Now, before that, let us see electrolysis of concentrated aqueous solution of sodium chloride. Okay. Electrolysis of concentrated aqueous solution of sodium chloride. Then electric current is passed through a concentrated aqueous solution of sodium chloride. Hydrogen gas is evolved at cathode and chlorine gas at the anode. So let us first see at cathode the reaction would be 2Cl minus aqueous. It will give 2 electron and it is reduce and it is the oxidation, right? And this is at anode. This is at anode. And at cathode, two H2O takes 2 electron and forms hydrogen gas and 2OH minus ion aqueous. This is reduction. So what is the overall reaction? Overall reaction is this overall reaction will be 2H2O liquid plus 2Cl minus aqueous will be Cl2 gas plus H2 gas plus 2H minus aqueous. See, Na plus ions are present in the solution, right? But they do not get reduced at the cathode. Now the question is why water molecules get reduced at the cathode in presence of Na plus ions, which are also present in the solution. So let us see why this is happening. See, in aqueous solution, NaCl ionizes as Na plus aqueous and Cl minus aqueous. Thus, the aqueous solution of sodium chloride contains both Na plus and Cl minus ions in addition to water molecules. The water molecules present in the solution are capable of undergoing both oxidation and reduction. Right? Because if we talk about water molecule, then 2H2O liquid can be O2 gas plus 4H plus aqueous plus 4E minus. This is oxidation. For 2H2O liquid, it takes 2 electron and gives H2 gas and 2H minus ion aqueous. This is your reduction. Thus, on passing electric current, there will be a competition between the ions, that is Na plus and Cl minus, and water molecules to undergo oxidation or reduction at a particular electrode. The preferential oxidation or reduction of a particular species at a particular electrode can be predicted with the help of standard electrode potential of the species present in the solution. Although the method has certain limitations, but somehow we can utilize this. The possibilities of reactions at the two electrodes in terms of electrode potential in our case. So let us discuss it. At cathode, At cathode, the reaction which occurs at cathode are reduction reactions, right? So in case of electrolysis of aqueous solution of sodium chloride, the following two reactions can occur at cathode. That is, at cathode it may be Na plus aqueous plus E minus 2Na, and standard reduction potential is minus 2.71 volt, and 2H2O liquid plus 2E minus can be H2 gas plus 2H minus aqueous, and standard reduction potential would be minus 0.83 volt. So a reduction reaction with a higher value of standard reduction potential must possess a greater tendency to occur at the cathode. Since the standard reduction potential of water is greater than greater means here less negative than that of Na plus ion, water molecule should get preferentially reduced at cathode in competition to Na plus ions. It actually happens. During the electrolysis of aqueous solution of NaCl, Na plus ion with a lower value of standard reduction potential are unable to get reduced at cathode and remain as such in the solution. On the other hand, water molecules having a higher standard reduction potential get reduced at cathode. Okay. The reduction of water molecule at cathode produces hydrogen gas. We have seen this. Produces hydrogen gas. Hydrogen gas thus formed gets liberated at the cathode. OH minus ion pass into the solution. This OH minus ion will pass into the solution and makes the solution alkaline. This is why the electrolysis of aqueous solution of sodium chloride is employed for the commercial preparation of NaOH. Remember this. This will come in your exam. And if we talk about anode, add anode, the reaction which occurs at anode are oxidation reactions, right? So in the present case, water and Cl minus ions have almost equal chances to get oxidized at anode under similar conditions. So if we write the equations, we can see that half O2 gas plus 2H plus aqueous plus 2E minus will give H2O. Standard reduction potential is 1.23 volt, or Cl2 aqueous plus 2E will give 2Cl minus. Standard reduction potential is 1.36 volt, right? Now, the species with a lower value of standard reduction potential should have a greater tendency to lose electrons and should get oxidized first at the anode. Water possesses a lower value of standard reduction potential as compared to that of chlorine and should get oxidized first at the anode. However, in concentrated aqueous solution of sodium chloride, the oxidation of Cl minus ions is preferred. The chlorine ions gets oxidized at the anode in preference to water molecules, and therefore chlorine is obtained at the anode in place of oxygen. And remember, this is for concentrated solution. Now, this is known as overvoltage. This unexpected result is due to overvoltage. Now, what is overvoltage? Remember this term, overvoltage. We should get this, but we actually get chlorine gas. Okay. The oxidation of water involving the liberation of oxygen requires some extra voltage in comparison to that expected theoretically. This is because of the large activation energy involved in the transfer of electrons from water to the anode. The energy barrier can be overcome by supplying an extra potential. The difference between the voltage actually required for the electrode reaction to occur and that expected theoretically is referred to as overvoltage. The oxygen overvoltage on platinum electrode is about 0.25 volt. Due to overvoltage, the oxidation of water can take place only at about 1.5 volt instead of 1.23 volt as expected theoretically. On the other hand, the oxidation of Cl- ion requires only 1.36 volt. Hence, the oxidation of Cl- ion is preferred in comparison to that of water. So, I think you have understood what is overvoltage and why we get chlorine gas at anode, not oxygen. This is due to overvoltage. Remember this will definitely come in your exam. And if you want to write, so slow it down and write the explanation I have given for overvoltage. Now let us see on the basis of these explanations. Now see what is the criteria for product formation. Criteria for product formation. Okay. Number one criteria is the substance which possesses higher standard reduction potential is reduced first at the cathode. Is the first point. The substance which possesses higher standard reduction potential is reduced first at the cathode. Remember this point. If the cation produced from the electrolyte in aqueous solution has higher reduction potential than that of water, the cation gets reduced at the cathode and the corresponding product is obtained. However, if the reduction potential of cation is less than that of water, water gets reduced at the cathode and hydrogen gas is liberated. The ions like Na+, Ca2+, Al3+ cannot be reduced in aqueous solution as their reduction potential are much lower than that of water. Therefore, water is reduced in preference to Na+, Ca2+, and Al3+. On the other hand, the ions like Cu2+ and Ag+ possesses higher reduction potential than that of water and gets reduced easily at the cathode in preference to water. Okay, remember these points. Number 2 points is the substance which possesses lower standard reduction potential. Lower standard reduction potential is oxidized first at the anode. If the anion produced from the electrolyte in aqueous solution has lower reduction potential than that of water, the anion will get oxidized at the anode in preference to water, and the corresponding product will be obtained at the anode. However, if the reduction potential of the anion is higher than that of water, water gets preferentially oxidized and O2 gas is liberated at the anode. See, the anions like Br minus and I minus have lower reduction potential than that of water and easily get oxidized at the anode to give Br2 and I2. On the other hand, F minus ion have much higher reduction potential as compared to that of water. This is why F minus ion do not get oxidized in the aqueous solution to give F2. In the aqueous solution of a fluoride, water gets preferentially oxidized and O2 is evolved at the anode. I think now you got the point why we get all these points. Now let us see. There may be other examples also. Okay. So there are other examples of electrolysis, that is electrolysis of aqueous copper sulfate solution using platinum electrodes. Okay, let's see this. Electrolysis of aqueous copper sulfate solution using platinum electrodes. See, in aqueous solution, copper sulfate ionizes as CuSO4 aqueous. This gives Cu2 plus aqueous and SO4 2 minus aqueous. When electric current is passed through the aqueous solution using platinum electrodes, copper is obtained at cathode while O2 gas is at the anode. Okay. Now let us explain these formations. At cathode, following reactions can occur, that is Cu2 plus aqueous plus 2A minus gives Cu solid. Standard reduction potential is plus 0.34 volt, and 2H2O liquid plus 2E minus, this will be H2 gas plus 2H minus aqueous. Standard reduction potential is minus 0.83 volt. So reduction potential of Cu2 plus is greater than that of water. So Cu2 plus ion will reduced in preference to water, and copper metal will deposit at the cathode. So at cathode, copper metal will deposit. Now if we talk about anode, there are two possibilities also. H2O liquid, this is half O2 gas plus 2H plus aqueous plus 2E minus. Standard reduction potential is plus 1.23 volt, and SO4 2 minus aqueous gives SO4 plus 2E, standard reduction potential is 2.0 volt. So reduction potential of water is less than that of SO4 2 minus. Okay, so water will preferentially oxidize at anode and O2 gas will be evolved. Okay, so this reaction will occur at anode, not this, and here not this. So the actual reaction occurring at electrode and the overall reaction. So at cathode, the actual reaction occurring is CO2 plus aqueous plus 2E minus gives Cu solid, and at anode H2O liquid will be half of O2 gas plus 2H plus aqueous plus 2A minus. So overall reaction will be CO2 plus, this is overall reaction. This will be CO2 plus H2O liquid. This will be Cu solid plus half O2 gas plus 2H plus aqueous. Now, if we see another example, because definitely from this one question will definitely come in your exam. So next is electrolysis of aqueous copper sulfate solution using copper electrode. So let's say this. Now, when electrolysis of aqueous copper sulfate solution is carried out using copper electrode, copper gets deposited at the cathode and an equivalent amount of copper from the anode dissolved into the solution as Cu2 plus ion. So at cathode, see, since the reduction potential of Cu2 plus, that is plus 0.34 volt, is greater than that of water, that is minus 0.83 volt. So Cu2 plus ion will gets reduced preferentially and copper metal gets deposited at the cathode. So it will be Cu2 plus aqueous plus 2E minus gives Cu solid. And at anode, the reactions, oxidation reaction occurs at anode, right? Now anode is made of copper, so it itself may also get oxidized. Thus at anode there is possibility of following reactions. So at anode there may be H2O liquid, that may be half O2 gas plus 2H plus aqueous plus 2E minus. Standard reduction potential is plus 1.23 volt. Okay, and SO4 2 minus aqueous and give SO4 plus 2E minus. Standard reduction potential is plus 2.0 volt. and copper solid, that is, this is from anode, gives Cu2 plus aqueous plus 2 electron, and standard reduction potential is plus 0.34 volt. So see, among these reactions, the reduction potential of copper is minimum. Therefore, the oxidation of anode that is made of copper is most probable. Thus, copper anode itself undergoes loss of electron to form Cu2 plus ions, which pass into the solution. Okay, so this is the reaction which will occur. Hence, on passing electric current in an aqueous copper sulfate solution using copper electrode, we have seen that at cathode Cu2 plus aqueous plus 2E minus will give Cu solid, and at anode Cu solid from anode will give Cu2 plus aqueous plus 2E minus. So on account of electrolysis, copper gets deposited at cathode and equivalent amount of copper from the anode dissolves into the solution as Cu2 plus ions. Thus the concentration of copper sulfate solution remains unchanged. Now let's see another example. Electrolysis of dilute aqueous H2SO4. Okay, so sulfuric acid ionizes as OH plus aqueous plus SO4 2 minus aqueous. On passing electric current, electrolysis takes place, and we can say that at cathode the following reactions may occur. It is 2H plus aqueous plus 2E minus. This may be hydrogen gas. Standard reduction potential is 0.00 volt, or 2H2O liquid plus 2E minus gives H2 gas plus 2OH minus aqueous, and E naught is minus 0.83 volt. Since H plus ions possesses a higher reduction potential, so H plus ion gets preferentially reduced and hydrogen gas is obtained at the cathode. So this is the reaction at cathode. And if we talk about anode, at anode again there are two possibilities. H2O liquid gives half O2 gas plus 2H plus aqueous plus 2E, and standard reduction potential is plus 1.23 volt, and SO4 2 minus aqueous is SO4 plus 2E minus, and standard reduction potential is plus 2.0 volt. Since the reduction potential of water is less than that of SO4 2 minus ion, so water will preferentially oxidized and oxygen will evolve at the anode. So this is the reaction at anode. Okay, now Moving forward to our next topic, which is extremely important, that is our quantitative aspect of electrolysis. Okay, so let us see. This is quantitative aspect of electrolysis. C. Michael Faraday in 1832 studied the phenomena of electrolysis extensively and established a relationship between the amount of products liberated at the electrodes and the quantity of electricity passed in the solution to carry out the electrolysis. He formulated two important quantitative laws which govern electrolysis, and these laws are known as Faraday's law of electrolysis. Remember, one question will definitely come from this section. So our first law, that is Faraday's first law of electrolysis. This law is the amount of substance, the amount of substance liberated or deposited at a particular electrode during electrolysis is directly proportional to the quantity of electricity, that is total charge passed in the solution. So this is the first law. The amount of substance liberated or deposited at a particular electrode during electrolysis is directly proportional to the quantity of electricity passed in the solution. So let us say that W gram of substance gets liberated at a particular electrode. Okay, on passing Q coulombs of electricity, this charge. So then according to first law, we can say W is proportional to Q. Now see, we know that Q is equals to I into T. So we can say that W is proportional to IT. And if we remove this proportionality, we will have W equals to ZIT. This Z is a constant, is known as electrochemical equivalent of the substance liberated at the electrode. So Z is a constant. It is electrochemical equivalent of the substance liberated at the electrode. So we can say that if current is 1 ampere, time is 1 second, so in that case W is Z. Hence, electrochemical equivalent may be defined as the amount of substance liberated by a current of 1 ampere passed for 1 second. This is the electrochemical equivalent. Okay. Now let us see our second law, that is Faraday's second law of electrolysis. And this law is when the same quantity of electricity is passed through the solutions of different electrolytes connected in series, the masses of the substances liberated or deposited at the electrode are directly proportional to their equivalent masses. Okay. So when the same quantity of electricity is passed through the solutions of different electrolytes connected in series, the masses of the substances liberated or deposited at the electrodes are directly proportional to their equivalent masses. So it's a very important law. Suppose 3 voltmeters connected in series. Okay. So let us see by one example. Let us say we have 3 voltmeters. This is 1, this is 2, and this is 3. Let's draw the diagram quickly. So connection will be from here to battery positive terminal. There is a resistance. So this is your plus, minus, plus, minus, plus, minus. This is your key. This is your rheostat. This terminal is connected like this. This terminal is connected like this. Okay. Now this is the connection. This is your AgNO3 solution, aqueous. This is CuSO4 solution, aqueous. This is dilute H2SO4 solution, aqueous. So suppose these 3 voltmeters are connected in series, contains aqueous solution of silver nitrate, copper sulfate, and dilute sulfuric acid. On passing electric current, electrolysis takes place in all the 3 cells, and the substances produced at the electrode of the cells are silver, copper, and hydrogen gas. Okay. Now, if the same current is passed for the same time, it is found that mass of silver deposited by mass of copper deposited is equals to equivalent mass of silver by equivalent mass of copper. Okay. And mass of hydrogen gas liberated by mass of silver deposited is equal to equivalent mass of hydrogen by equivalent mass of silver. These results are in accordance to the above statement. So this verifies the second law of electrolysis. If W1 and W2 are the masses of the substances liberated by passing the same quantity of electricity, and E1 and E2 are their equivalent masses respectively, then according to Faraday's second law of electrolysis, we can say that W1 by W2 is E1 by E2. If Z1 and Z2 respectively are the electrochemical equivalents of the two substances and I is the current passed through 3 seconds, and from first law you know that W1 is Z1 IT and W2 is Z2 IT. So if we put the values here, it will be Z1 IT by Z2 IT is E1 by E2. Okay, so this IT and IT will cancel out, so we can say Z1 by Z2 is E1 by E2. That means E is proportional to Z, and we can say E is F into Z. There is a constant. F is a constant and known as Faraday's constant. This F is your Faraday's constant. Okay, and so we can say that here F is a constant and 1 Faraday is the charge carried by 1 mole of electrons. 1 Faraday is the charge carried by 1 mole of electrons. So you can say F is Na into E, and this value of F is 96,500 coulombs. Okay, so from this equation we can say that Z is E by F. Okay, so Z is electrochemical equivalent is, that is, we can say that equivalent mass over Faraday's constant, that is equivalent mass upon 96500 gram per coulomb. Okay, now this equation or you can say this equation helps us to find the electrochemical equivalent of a substance, and unit is gram per coulomb. Now let us see one question. The question is, the current of 0.2 ampere is passed in aqueous solution of copper sulfate for 1 hour. Calculate the mass of copper deposited at the cathode. Okay, so let's see the solution of this. See, atomic mass of copper is 63.5 and valency of copper in CuSO4 is 2. So what is the equivalent mass of copper? So we can say equivalent mass of copper is atomic mass by valency. So this is 63.5 by 2. That is 31.75 is the equivalent mass of copper. Now we know that electrochemical equivalent Z is equivalent mass upon 96500. So this is 31.75 upon 96500. This is 3.29 into 10 to the power minus 4 gram per coulomb. Okay. Now see, here in the question it is given that current is 0.2 ampere. Okay, for 1 hour it is passed. So current is 0.2 ampere. Time is 1 hour. That is 3600 seconds. So from first law we know W is equals to ZIT. So Z we have calculated 3.29 into 10 to the power minus 4. I is 0.2 and T is 3600 seconds. This value comes out to be 0.2369 gram. Okay. So mass, this much mass is deposited at cathode. So let us see another question regarding this. How long a current of 3 ampere has to be passed through a solution of silver nitrate to coat a metal surface of area 80 centimeter square with a 0.005 millimeter thick layer, and it is given that density of silver is 10.5 gram per centimeter cube. So let's see the solution. So see, volume of the silver layer to be deposited is, we can say, this is area multiplied by thickness. So area is 80 centimeters square, and what is the thickness? Thickness is 0.005 millimeter. That is 0.005 by 10 centimeter. This value comes out to be 0.04 centimeter cube. So what is the mass of silver deposited? Mass of silver to be deposited, you can say density multiplied by volume. So 10.5 is the density given, multiplied by 0.04. This is 0.42 gram. Now equivalent mass of silver is atomic mass upon valency. So this is 108 by 1. This is 108. And we know the relation that Z is equivalent mass. Z is equivalent mass over 96500. That is 108 by 96500. It should be 1.12 into 10 to the power minus 3 gram per coulomb. From first law we can say W equals to ZIT. So this T should be W by ZI. W is 0.42, Z is 1.12 into 10 to the power minus 3, and current is 3 ampere. So it is 124.99 second. This is the answer. The quantitative aspect of electrolysis can be discussed with the help of Faraday's law. See, we know that Faraday's second law of electrolysis implies that the same quantity of electricity can liberate chemically equivalent amounts of all substances, right? So let us find out the quantity of electricity required to liberate one equivalent of any substance during electrolysis. So according to first law of Faraday, we know W equals to ZIT. So from this we can say that Z is W by IT. Okay. Now if we put this value, and we know another relation, that E is F into Z. So if we put this value into this equation, this will be E is F into W by I into T. Okay. So from this we can say W is E I T by F. Okay. Now let us say if I into T is 1 farad, then this farad and this farad will cancel out. We can say that W is E, right? Thus, on passing a charge equal to 1 Faraday, that is Q equals to IT, right? So if we pass charge equivalent to 1 Faraday, that is 96,500 coulomb in the solution of an electrolyte, the amount of substance liberated is equal to its equivalent mass. Hence, we can conclude that the quantity of electricity required to liberate one equivalent of any substance is 1 Faraday. Okay. Now see, one equivalent of any substance can be liberated at a particular electrode only when the corresponding species either gains or loses electrons, loses 1 mole of electrons. So we can say that A plus aqueous, this is one equivalent plus E, this is 1 mole of electron, it will be K, that is 1 equivalent. Okay. Now if we say B minus aqueous, this is 1 equivalent, and if it is B 1 equivalent, then it will liberate 1 mole of electron. 1 mole of electrons. Now this is your reduction at cathode. This is your oxidation at anode. Since 1 equivalent of any substance requires 1 Faraday of electricity to get liberated at a particular electrode, 1 Faraday must be the charge carried by 1 mole of electron, right? So we can say that 1 Faraday is charge carried by 1 mole of electron. Okay, we can say that charge carried by an electron multiplied by Avogadro number. Multiply by Avogadro's number. Now we know charge on an electron, that is 1.60 into 10 to the minus 19 coulomb, and Avogadro number is 6.02 into 10 to the power 23. So if we multiply, we will get 96472.44 coulomb per mole, right? So hence we can say 1 Faraday is 96472.44 coulomb per mole, or approximately 96500 coulomb per mole. Okay, so if an electrode reaction involves n moles of electrons and the total quantity of electricity Q involved in the reaction, so we can say Q is actually N into F. Okay, N is N moles of electron. Moles of electron. Okay, so knowing the moles of electron involved in electrode reaction, the quantity of electricity passed can be determined. Further, the mass of substance produced in the reaction can be calculated with the help of Faraday's law of electrolysis. Okay, let's say in the electrode reaction, in the electrode reaction, Na plus aqueous 1 mole plus electron 1 mole gives Na solid 1 mole. So 1 mole of Na plus, that is we can say 1 equivalent, requires 1 mole of electron to get reduced. Hence, the quantity of electricity needed for the reduction of 1 mole of Na plus ions to give 1 mole of Na solid is 1 farad. Right? Let us take another example. In the electrode reaction, Cu2 plus aqueous plus 2E minus Cu solid. Okay. So from this we can say that 1 mole of Cu2 plus, that is here 2 electron is transferred, so 2 equivalents, right? So in this case 2 equivalent, 1 mole of Cu2 plus means 2 equivalents. Requires 2 moles of electron, 2 moles of electron to get reduced. Hence, the quantity of electricity required to reduce 1 mole of Cu2 plus ion is 2 farad. Okay, because our definition is Q equals to N into F. So here N is 2 mole, right? Let us see another example. We take the electrode reaction as Al3 plus plus 3E minus gives Al. So here we can see that 1 mole of Al3 plus, that is 3 equivalent of Al3 plus, requires 3 moles of electron. Hence, the quantity of electricity needed to reduce 1 mole of Al3 plus will be 3 farad. Okay, I think you got the point how to calculate this. So, let us see one question. How much charge is required for each of the following reduction processes? 1 mole of Al3 plus to Al. Number 2 is 1 mole of Zn2 plus to Zn. Number 3 is 1 mole of MnO4 minus to Mn2 plus. Now see, we just have seen that Al3 plus 3E gives Al. So 1 mole of Al3 plus requires 3 moles of electron. So the amount of charge required here, in this case we can say amount of charge required is 3 farad. That is 3 into 96500 will be 289,500 coulomb. That's how you have to calculate. Now if we take number 2, 1 mole of Zn2 plus gives Zn. So Zn2 plus, this is 1 mole. It will take 2 moles of electron, gives Zn. So what will be the amount of charge required? That is 2F, right? The amount of charge required is 2F. It is 2 into 96,500. This much coulomb. Now if we talk about number 3, the electrode reaction would be MnO4 minus plus 8H plus 5E gives Mn2 plus 4H2O. Now this is 1 mole of MnO4 and here we can see that this is 5 moles of electron. So 1 mole of MnO4 requires 5 moles of electron. That means the charge required is 5F. So 5 into 96500. This will be 482500 coulomb. Okay. Now let's see our next question. How many coulombs are required for the following oxidation process? Number 1 is 1 mole of FeO to Fe2O3, and number 2 is 1 mole of H2O to O2. Now if we talk about this, the electrode reaction of 1 mole of FeO, we can write it as FeO plus half O, that is half of Fe2O3. Okay. Now we can say in this manner also, Fe2 plus, this is 1 mole, gives Fe3 plus plus 1 mole of electron. So it is clear that 1 mole of FeO losses 1 mole of electron, right, to get oxidized to Fe2O3. Hence, quantity of electricity required is 1 farad, that is 96500 coulomb. Now let's see this question. 1 mole of H2O2O2. So reaction is H2O liquid. This is 1 mole gives half O2 gas plus 2H plus aqueous plus 2E. This is 2 mole. So 1 mole of H2 gives 2 mole electron. During oxidation, so electricity required is 2F. That is 2 into 96500. So 193,000 coulomb. Okay. Now let's see another question. Our next question is calculate the number of coulombs required to deposit 6.75 gram of aluminium when electrode reaction is L3 plus 3E gives L. Given atomic mass of Al is 27 gram per mole, and we know the value of F is 96,500 coulomb. So let us see our electrode reaction is given L3 plus 3E gives Al. So that means 1 mole of Al3 plus takes 3 moles of electron to give 1 mole. So it indicates that 1 mole, that means 27 gram of aluminium requires 3 moles of electron. 1 mole, that is 27 gram aluminium, requires 3 moles of electron. That is the charge required to deposit 27 gram of aluminium is 3 moles of electron, right? So you can say charge required to deposit 27 gram of aluminium is 3 farad, or 3 into 96500. Okay. So what is the charge required to deposit 6.75 gram of aluminium? So 27 gram requires this much charge. So 1 gram will require 3 into 96500 by 27, and 6.75 gram of aluminium requires 3 into 96500 by 27 multiplied by 6.75. If you calculate, it will be 72375 coulomb. Okay. So let us see another question. How many hours does it take to reduce 3 moles of Fe3 plus to Fe2 plus with 2 ampere of current? So let's see the solution. Now what is the reaction? It will be Fe3 plus E gives Fe2 plus. So this is 1 mole. This is also 1 mole. So from this equation, it is clear that 1 mole of Fe3 plus, I only require 1 mole of electron for reduction. So quantity of electricity required to reduce 3 moles of, because we have to reduce 3 moles of Fe3 plus, that will be 3 farad, right? 1 mole required 1 mole electron. So 3 moles will require 3 moles. So that means 3 farad. So Q charge required to reduce 3 moles of Fe3 plus ions is 3F. It is 3 into 96500. 289500 coulomb. Now you know Q equals to IT. That means Q time T would be Q by I. This is 289500 divided by 2. Okay. So it will be 1444750 second. That means 40.21 hours. It will require 40.21 hours to reduce 3 moles of Fe3 plus to Fe2 plus. Now our next topic is batteries. Some commercial cells and batteries. Okay. See, a galvanic cell, that is an electrochemical cell, converts the chemical energy of a galvanic cell, electrochemical cell, converts the chemical energy of a redox reaction into electrical energy. Thus, a galvanic cell constitutes a source of electrical energy. In principle, any redox reaction can be used to generate electrical energy in a galvanic cell, but practically it is not possible to use most of the redox reactions for the generation of electrical energy in a galvanic cell. Only a few redox reactions have been found suitable for the construction of commercial cells. The commercial cells are popularly known as batteries. The term battery is not strictly correct when used to refer a single cell. In true sense, a battery is an arrangement of two or more galvanic cells connected in series. So what's the battery? Battery is a arrangement of two or more galvanic cells connected in series. Connected in series is a battery. Now remember, the commercial cell or battery should meet some conditions. Number one is it should be light in weight and compact in size. Number two, its voltage should not vary appreciably during the use. Number three is it should have a reasonably long life. Now if we divide batteries, commercial cells or batteries, that can be divided into two types. One is primary cell, another is secondary cell. Okay. Now let's see what is primary cell. So let's talk about primary cell. The primary cells are those cells in which the cell reaction occurs only in one direction and the reaction cannot be reversed by the external energy source. Okay, remember this. Primary cells, I'm again repeating, primary cells are those cells in which the cell reaction occurs only in one direction and the reaction cannot be reversed by the external energy source. Thus, in primary cells, the reaction occurs only once, and after a certain period of time, the battery becomes dead and cannot be used again. Such cells cannot be recharged. If we take some example of primary cells, these are Daniel cell, dry cell, mercury cell, these are your primary cells. Okay. Now, in examination, वो लोग तुमको रिएक्शन लिखने के लिए देता है कि बोलो इस बैटरी में क्या रिएक्शन होता है. So let's see one by one. Our first primary cell is dry cell or lactulence cell. Lactulence cell. Dry cell are the most familiar type of commercial cells, right? And it's a compact form of lactulence cell. A dry cell, let us say, let's see the diagram of dry cell. So I'm drawing a rough diagram in order to understand what it is. Okay, it consists of a zinc metal container which works as anode. Okay, this is your zinc metal container. It acts as anode. This is your zinc container. It acts as anode. A graphite rod surrounded by powdered MnO2 and carbon acts as cathode. So here in this region, we have MnO2 and carbon. Okay, and this is your graphite rod. This thing is your graphite rod. And it works as cathode. So the space between the zinc container anode and the graphite rod cathode is filled with a moist paste of NH4Cl and ZnCl2. Okay, this region is filled with NH4Cl plus ZnCl. The zinc metal container is wrapped with a cardboard cover or thick paper lining. The cell is sealed on the top with a pitch or wax. Okay, this is the pitch or seal. Okay, this thing is your pitch seal. The electrode Now, the electrode reactions involved during the operation of the cell are complex. However, the approximate reactions can be shown at anode. The approximate reaction is ZnS gives Zn2 plus 2E minus. And at cathode it will be MnO2 plus NH4 plus E minus gives MnO OH plus NH3. Okay, this is the approximate reaction. At anode, zinc from the container gets oxidized to Zn2 plus. At cathode, manganese is reduced from plus 4 state to plus 3 state. This is in the plus 4 oxidation state to this is in the plus 3 oxidation state. Ammonia produced in the cathode reaction combines with Zn plus 2 ions liberated in the anodic reaction to form ZnNH3 4 plus ion. Okay, this thing and ammonia will give ZnNH3 4 plus ion. The complexation of Zn2 plus by NH3 molecule decreases the concentration of free Zn2 plus ions. This increases the voltage of the cell. So the cell potential of a dry cell is approximately 1.25 volt to 1.5 volt. Dry cell do not have a long life because NH4Cl paste used in a dry cell is acidic in nature and corrodes the zinc container even when not in use. A dry cell is a primary cell and cannot be recharged. So that's all about dry cell or lacular cell. Now, our number 2 is mercury cell. Mercury cell is a new type of dry cell. It's a new type of dry cell and is very convenient source of electrical energy for applications having small electrical circuits such as watches, camera, hearing aids, etc. It consists of zinc mercury amalgam as the anode, paste of mercuric oxide and carbon act as the cathode. The electrolyte used in the cell is a paste of KOH and ZNO. When the cell is operated, the reactions are as follows. At anode, we can say the reaction is zinc amalgam plus 2OH minus gives ZNO solid plus H2O plus 2E. And at cathode, HGO solid plus H2O plus 2E gives Ag plus 2OH minus. So the overall reaction could be zinc amalgam plus HGO gives ZNO solid plus Hg liquid. See, in this net reaction, it does not involve any ion in solution whose concentration may change, right? It does not contain any ions. Therefore, the potential of the cell remains constant, not only during its operation but throughout its life. The cell potential of mercury cell is approximately 1.35 volt. That's why it is so important. Now, let's talk about secondary cells. Secondary cells. So the cells which can be recharged by passing a direct current through them are called secondary cells, and these are repeated action cells. After every use, they can be recharged and thus can be used again and again. Secondary cells are also called storage cells or accumulator. This is called storage cell or accumulators. Okay, because they are capable of storing electrical energy in the form of chemical energy. If we take some example of secondary cells, these are lead storage cell, lead storage cell, nickel cadmium cell. Okay, now let us see our first example. which is lead storage battery. It is the most commonly used battery in automobiles, that is cars, buses, trucks, and in household power inverters is lead storage battery. It consists of a number of lead storage cells, usually 6 or 12, connected in series. A lead storage cell is a galvanic cell in which anode is made of a grid of lead or an alloy of lead and antimony, packed with finely divided spongy lead, while cathode is a grid of lead coated with red-brown lead dioxide, that is PbO2. The electrolyte is an aqueous solution of sulfuric acid, 38% by mass, having density of 1.3 gram per milliliter. And if we represent a lead storage battery, it can be represented by this PbSO4 solid. This is your anode side. H2SO4, this is 38% by mass. PbO2 solid Pb. This is your cathode side. The cell potential of a lead storage cell is 2 volts. Okay. So a lead storage battery is constructed by connecting a number of lead storage cells in series. A battery consisting of 6 cells gives an EMF of 12 volt. In order to obtain an EMF of 12 volts, 12 cells need to be connected together in series. In a lead storage battery, the anode and cathode plates, called grids. Anode is lead grids packed with finely divided spongy lead, and cathode is lead grid coated with PbO2, are arranged alternately and are immersed in a bath of 38% sulfuric acid solution. Okay. Now, let us say let us see the diagram first. Okay. So the rough diagram is something like this. There will be six. There will be another 6. These are connected. This is a rough diagram I am drawing. The diagram may look odd, but it is exactly look like this. This connected. This is anode, is negative. This is cathode, is positive. And cathode is this. This is your cathode. These are connected. These are connected. These are connected in this manner. Okay. This is the overall diagram. Sorry. These are, so here anode is lead grit packed with finely divided spongy lead, and cathode is lead grit coated with PbO2, are arranged alternately and are immersed in a bath of 38% sulfuric acid solution. The container is made of a tough insulating material. Here we have as a solution dilute H2SO4. This is 38% by mass. Okay. This is your, this side is your positive plate. This is positive plate. That is cathode. These are lead grit. These are lead grits coated with PbO2. And these are your, you can distinguish them by different, just say this, this. These are your negative plates. Anode. And these are lead grits packed with spongy lead. Okay. Now the container is made of a tough insulating material. The anode and cathode plates are separated from each other by separators made of some insulating material. The anode and cathode plates are separately connected to one another. This increases the surface area of the electrode and hence the current producing capacity of the battery. Okay. When current is drawn from the battery, following electrode reactions take place in each cell. And if we see the reaction will be at anode. Here are the following reactions. Is lead solid plus SO4 2 minus aqueous gives PbSO4 solid plus 2 electron. And at cathode it is PbO2 solid plus SO4 2 minus solid plus 4H plus aqueous plus 2E gives PbSO4 solid plus 2H2O. So the overall reaction would be Pb solid plus PbO2 solid plus 4H plus aqueous plus 2SO4 2 minus aqueous gives 2PbSO4 solid plus 2H2O. Okay. The electrode reactions and the overall cell reactions clearly indicate that sulfuric acid gets used up during the discharge of the cell. Therefore, when current is drawn from the cell, sulfuric acid gets diluted and its specific gravity falls. Both the electrodes get coated with the white precipitate of lead sulfide, that is PbSO4. When the specific gravity of sulfuric acid falls below 1.2 gram per centimeter cube and both the electrodes gets covered with PbSO4, the cell reaction stops and the battery is said to be discharged. At this stage, the cell or battery needs recharging. So if we see the recharging action, that is recharging of a discharged cell or battery so the discharged lead storage cell or lead storage battery can be recharged by passing a direct current through it in the opposite direction. So for this purpose, the negative electrode of the storage cell is connected to the negative of the DC source and the positive electrode of the cell to the positive of the DC source. The direct current thus passed reverses the electrode reactions and converts lead sulfate back to lead at the negative electrode and to lead dioxide at the positive electrode. The reactions taking place at the free electrode during recharging, and if we say the recharging action, the reaction would be as follows. At negative at negative electrode, PbSO4 solid plus 2 electron, you are giving direct current, so it will be PbS plus SO4 2 minus. At positive electrode, PbSO4 plus 2H2O gives, if you give DC current, then it will be PbO2 solid plus 4H plus aqueous plus SO4 2 minus aqueous plus 2E. So the overall reaction would be to Pb to Pb SO4 solid. This is present on the electrode, right? This is present on the electrode plus 2H2O. This is charging. So Pb solid plus PbO2 solid. Now this is that electrode materials recovered, right? This is electrode materials recovered plus 4H plus aqueous plus 2SO4 2 minus aqueous, and this is your H2SO4 reformed. So from this reaction it is clear that during the recharging of the cell, the electrode materials are restored in their original forms. Due to formation of H plus and SO4 2 minus ions, the specific gravity of sulfuric acid increases and it attains its original value 1.3 gram per milliliter. And the cell or thus battery thus becomes ready for the reuse. And if it discharges again, you can recharge in this process. Now, our next secondary cell is nickel cadmium storage cell. This is also called NiCad cell, nickel cadmium cell. Okay. The nickel cadmium storage cell or nickel cadmium accumulator is also a rechargeable cell. Although it is more expensive as compared to lead storage cell, yet it is becoming more and more popular because it is smaller, lighter, and has a longer life. It is suitable for portable and cordless appliances. The nickel cadmium storage cell, the anode is made of cadmium. Okay, this anode, this is anode, is made of cadmium, and cathode consists of a metal grid containing nickel oxide, and cathode is nickel oxide. Okay, cathode is nickel core oxide. The electrolyte is a solution of KOH. Okay, when the current is drawn from the cell, the reactions occurs is something like this. At anode, is the thing you have to remember because in the exam they will ask you about anode reaction and cathode reaction. That's all. And what is the electrolyte? What is used as anode? What is used as cathode? That's all you have to remember. So CD solid plus 2OH minus aqueous gives CdOH whole 2 solid plus 2 electron, and at cathode NiO2 solid plus 2H2O liquid plus 2E minus gives NiOH whole 2 solid plus 2H minus aqueous. And if we see the overall reaction, this would be CD solid, NiO2 solid, 2H2O liquid gives CDOH whole 2 solid, NiOH whole 2 solid. The cell has a potential or EMF of about 1.4 volt. As a cell reaction consumes water as the electrolyte, right? Water as the electrolyte. The voltage of the cell remains fairly constant during use. Moreover, the cell reaction does not involve any gaseous products. The products formed stick to the electrodes and can be recovered into substances originally present before the discharge of the cell by recharging process. A discharged cell can be recharged by passing a direct current in the opposite direction when cell reaction gets reversed and original substances get recovered at the electrode. Now, our next type of cell is fuel cell, and this is very important. Fuel cell. The cell which converts the chemical energy of a fuel directly into electrical energy are called fuel cells. In these cells, fuels like hydrogen, carbon monoxide, methane, C3H8 are used to generate electrical energy. The fuels are continuously supplied and the products are continuously removed. A large number of fuel cells are available. Among these, the most common one is hydrogen oxygen fuel cell. Okay, so let's talk about hydrogen oxygen fuel cell. Hydrogen oxygen fuel cell. This is also known as Bacon cell. Bacon cell. This is designed by Bacon. Hydrogen oxygen fuel cell is designed by Bacon in 1959. Therefore, it is known as Bacon cell. It is a potential source of electrical energy and was used as a primary source of electrical energy in the Apollo space program of USA. So you can imagine how much important topic is this. So let us first draw the fuel cell diagram. Drawing a rough diagram. So, this is a simple hydrogen oxygen fuel cell. The cell consists of two porous carbon electrodes. Okay, this is your carbon electrode and this is your carbon electrode. This is your porous carbon electrodes. Okay, impregnated with suitable catalyst such as platinum, silver, cobalt oxide. Okay, the space between the two electrode is filled with a concentrated solution of KOH or NOH. Okay, here in this space we have either NOH or KOH. Okay, which serve as an electrolyte. H2 gas and O2 gas are bubbled in the electrolyte through porous carbon electrodes. And in this cell, the reactions at anode is something like this. At anode, reaction is H2 gas plus 2OH minus aqueous gives 2H2O liquid plus 2E. This is multiplied with 2. We will require in for overall reaction. At cathode, this is O2 gas plus 2H2O liquid plus 4E. This will be 4OH minus aqueous. So the overall reaction is 2H2 gas plus O2 gas. It will give 2H2O liquid. Thus, the overall cell reaction involves the combination of hydrogen gas and oxygen gas to form water. The cell runs continuously as long as the reactants H2 and O2 are supplied. And it operates efficiently in the temperature range 343 Kelvin to 413 Kelvin, that is 70 degrees Celsius to 140 degrees Celsius, and provides a potential of about 0.9 volt. Okay, this cell was used as a source of electrical energy in Apollo space program. The water vapors produced in the cell reaction were condensed and water thus formed was used as drinking water by the astronauts. So see how much usable this thing is. Now what is the advantage of fuel cell? Fuel cells are the potential source of electrical energy and have an edge over the conventional galvanic cells and the conventional methods used for the production of electrical energy by burning the fuel. First advantage is high efficiency. Since fuel cells convert the energy of a fuel directly into electrical energy, they are potentially more efficient than the conventional methods used for the production of electrical energy by burning fuels such as hydrogen carbon fuels or by using nuclear reactors. Theoretically, fuel cells should be 100% efficient, but so far an efficiency of 60 to 70% has been attained. The efficiency of a conventional method involving the burning of a fuel is only about 40%. Now next advantage is pollution free working. The byproducts obtained from a fuel cell do not cause any pollution problem. In hydrogen oxygen cell produces only water, which is no way can cause pollution. Number 3 is continuous supply of energy. Fuel cell can supply energy continuously so long as the fuels are fed into them. Contrary to conventional cells or batteries, these cells do not involve any drop in the voltage or currents during long use. And if we talk about limitations, the handling of gaseous fuels is difficult. The fuel gases such as hydrogen, oxygen are required to be stored as liquids at very low temperature and high pressure in specially designed cylinders. This increases the cost of the cell and involves several practical difficulties. Number 2 is the catalyst needed for the electrode reactions such as platinum, lead, silver are quite expensive and increase the cost of the cell. Number 3 is the electrolytes used in fuel cells are highly corrosive and create several practical problems. Now, let us see our last topic of this chapter. After that, we will wrap up this chapter. This is corrosion. This is our last topic. See, when a metal is exposed to certain environment, it may get deteriorated due to its reaction with the environment and its surface may become rough. This phenomena is called corrosion. It is a common experience that most of the metals are affected in some way or the other when exposed to the atmosphere. The gases present in the atmosphere react with the metal and slowly deteriorate it. A large number of metals lose their shine due to deposition of the compounds such as oxides, sulfides, sulfates, carbonates, etc. on their surface. Some metals lose their strength and become weak and brittle. The tarnishing of silver, that is loss of shine, rusting of iron, deposition of a brown colored layer on its surface, development of green coating on copper and bronze, tarnishing of aluminium are the examples of corrosion. Corrosion is a wide term and not only includes the deterioration of a metal by atmospheric change, but in fact the deterioration of a metal by any environment surrounding the metal is covered by this term. So corrosion may be caused by gases, by liquids, by solutions present around the metal. So we can define corrosion as the slow but spontaneous deterioration of metal due to their interaction with certain environment is called corrosion. Now if we talk about the factors which govern the corrosion, it depends on several factors, and number 1 is reactivity of metal. A reactive metal is more susceptible to corrosion as compared to a less reactive metal. If we take example, iron corrodes faster as compared to silver because the former is more reactive, that is iron is more reactive. The reactivity of metal depends upon its electropositive nature. A more electropositive metal having a lower value of standard reaction potential is more reactive. Thus, the metals placed higher in the electrochemical series, that is sodium, calcium, magnesium, all this, corrodes faster, while metals placed lower in the electrochemical series, that is silver, mercury, are less susceptible to corrosion. Number 2 point is presence of impurities in metal. Pure metals usually do not corrode much. It is the presence of other metals, that is impurities, which compels the host metal to undergo the corrosion process. This is because the lesser electropositive impurity metal set up local galvanic cells with a host metal and oxidize the more electropositive host metal, which results in the corrosion of the host metal. Number 3 point is presence of reactive gases in air. Reactive gases such as carbon dioxide, sulfur dioxide, nitric oxide present in air dissolve in water and produce acids. The acids thus formed act as electrolytes and accelerate the process of corrosion. The number 4 point is presence of electrolytes in water. Presence of electrolytes in water increases the rate of corrosion. For example, corrosion of iron takes place to a greater extent in seawater as compared to that in distilled water. This is because the seawater contains several electrolytes such as NaCl, KCl, etc. Now, under corrosion, we will focus on rusting of iron. Rusting of iron. We will focus in this topic. Okay. Now, let us see what is rusting of iron. Rusting of iron is a specific case of corrosion. When a piece of iron is left exposed to moist air, it gets converted with a reddish brown coating. This coating can easily be scratched and is called rust. The phenomena of deposition of reddish brown coating on the surface of the iron by the action of moist air is called rusting, and the reddish brown coating is called the rust. So I think now you come to know what is rusting and what is rust. In fact, the rusting of iron is due to the combined action of air, water and carbon dioxide on iron. Perfectly dry air or pure air, free water does not cause rusting. The exact composition of the rust depends upon the atmospheric conditions and the relative contributions of the factors which govern rusting. Okay, but remember, it mainly consists of hydrated ferric oxide. It mainly consists of hydrated ferric oxide. This is Fe2O3 dot XH2, and its formation can be roughly estimated as 4Fe solid is iron, 3O2 gas, and this oxygen comes from air, plus 2xH2O, and this water vapor comes from air and will give 2Fe2O3 dot XH2 solid. This is your rust. The outer surface of iron first gets rusted in the presence of moist air, and a layer of hydrated ferric oxide, this is hydrated ferric oxide, is deposited on the surface. This layer is soft and porous and may fall off when it becomes sufficiently thick. This exposes the lower layer of iron to the atmosphere, which in turn gets rusted. The process continues and gradually iron loses its strength. Now, The factors which govern the rusting is presence of air, presence of moisture, presence of carbon dioxide, presence of impurities of lesser electropositive metals in iron, and presence of electrolytes in water. These are the factors. And if you want to prevent from corrosion, you can use coating of metal surface, or you can use paint. You can use grease or oil. Non-corrosive metal, you can use coating of non-corrosive metal, and you can use some certain chemicals which stops rusting. Okay, now these are the processes. Now I think you have understood this chapter. This is the overall reaction involved in the rusting process, and we are here omitting the mechanism of rusting, because in your exam they will only ask short questions. What is rusting? How to prevent rusting? All this. What is corrosion? So I think that's all for today. ये जो चैप्टर है तुम लोगों को समझ में आया होगा. बहुत इंपॉर्टेंट चैप्टर है इलेक्ट्रोकेमिस्ट्री, और इसमें से हर एग्जाम में जरूर क्वेश्चन होता है. तो अगर ये वीडियो तुम लोग अच्छा लगे तो लाइक करो, सब्सक्राइब करो और अपने दोस्तों से शेयर करो, क्योंकि जब लाइक देखता हूँ और सब्सक्रिप्शन बढ़ता है तो वीडियो बनाने का ज़्यादा इच्छा होता है, और लगता है कि तुम लोगों के लिए और भी ज़्यादा वीडियो बनाऊँ. सो दैट्स ऑल फॉर टुडे एंड हैव ए गुड डे.